me permitiría hacer algunos comentarios en inglés debido a que hay participantes internacionales. Agradecemos la presencia de todos los asistentes que nos acompañan de manera presencial y a quienes nos están siguiendo vía streaming. Y también queremos expresar nuestro agradecimiento a los estudiantes, profesores y todo el personal académico y administrativo que hicieron posible la infraestructura necesaria para el desarrollo de este evento. Además, queremos hacer una mención especial al capítulo estudiantil de la IEEE, Solid State Circuit Society de la UIS, con el apoyo especial del Grupo de Investigación on Chip. Good morning, everyone. It's a pleasure to welcome you to this event. We would like to thank all the participants attending in person and those joining us via streaming. We'd also like to thank the students, professors, and staff who made this event even possible. I would like to give special mention to the WIS chapter of the IEEE Solid State Circuit Society with the support of the On-Chip Research Group. La IEEE Solid State Circuit Society es una de las sociedades más reconocidas a nivel mundial en el área de diseño de circuitos integrados y sistemas electrónicos, promoviendo la investigación, el desarrollo tecnológico y además la formación de ingenieros en el área de la microelectrónica. La UIS, a través del Grupo de Investigación on Chip, ha sido líder en Colombia en el área de circuitos integrados por ya varios años y ha llegado a contribuir significativamente a la formación de talento humano y desarrollo de investigación a muy alto nivel. Y de hecho fue la primera universidad en Colombia en contar con el capítulo estudiantil de la IEEE Solid State Circuit Society, lo cual resalta su compromiso con la excelencia. Este evento es una iniciativa estudiantil que busca acercar la comunidad académica y profesional a temas de circuitos integrados, diseño microelectrónico y tecnologías del estado sólido. The IEEE Solid State Circuit Society is a globally recognized community dedicated to the advancement of integrated circuits and microelectronic systems. The Universidad Industrial de Santander, through On-Chip Research Group, has been a national leader in integrated circuits research for a long time, and was the first institution in Colombia to even establish the IEEE Solid State Circuit Society as a student chapter. This event is an initiative led by students with the purpose of bringing the community close to modern topics in integrated circuits. A continuación les explicaremos brevemente la estructura del evento. El evento estará dividido en sesiones de charlas técnicas impartidas por los ponentes, invitados, y cada charla tendrá una duración de aproximadamente 1 hora 35 minutos, seguida de un espacio de 15 minutos para preguntas y discusión. Las preguntas podrán realizarse al final de cada ponencia y para los asistentes presenciales pueden levantar la mano y los asistentes en línea podrán escribir por medio del chat. Tendremos un coffee break aproximadamente a las 10 de la mañana, sin embargo, durante cada charla el mismo ponente se encargará de mencionar para hacer la pausa del coffee break. Y en cuanto al idioma, algunas charlas se van a realizar en inglés y otras en español. En particular, la que iniciaremos ahora será en inglés. This talk will cover the fundamentals and variants of asynchronous control, emphasizing its advantages under low voltage and high variability conditions. Now let me introduce you to our first speaker. Professor Makoto Ikeda received his BE, ME, and PhD degrees in electrical engineering from the University of Tokyo in 1991, 1993, and 1996, respectively. He joined the University of Tokyo as an associate researcher in 1996, and he is currently a professor and director of the Systems Design Laboratory, also known as the Lab, at the same institution. And in parallel, he has been actively involved in activities of the VLSI Design and Education Center, where he has promoted education and research in VLSI design within the Japanese academic community. His research interests include hardware security, asynchronous circuit design, intelligent sensor for 3D sensing, and time domain signal processing. He has held leadership roles in major international conferences such as SSCS and the VLS Circuit Symposium. Professor Ikeda is a senior member of the IEEE and IEICE Japan and member of IPSJ and AECM. The title of this talk is Basics of Asynchronous Circuit Design. Please join me in welcoming Professor Makoto Ikeda.
Buenos dias. Good morning, everyone. Thank you very much for joining my talk today, this morning. So it is very honor for me to be here. Actually, this is my first time to come to Colombia as well as Bucaramanga. So I'm very happy to be here. And also it is already introduced, but I'd like to start a bit introducing about what solid-state circuit society is. So this is organized by solid-state circuit society chapter, and so we are the sort of the hosting society, and IEEE solid-state circuit society is the organizing this or the hosting several international conferences, including SSCS, which is the flagship conference for us, and also UIS held in San Francisco every year in February, and UIS Symposium, which is jointly organized by the United States and Japan, and which is held in June in Hawaii and Kyoto. And also we have the Asian Solid-State Circuit Conference, which is organized in November. They're rotating around Taiwan, Korea, China, and Japan. Also we organizing the SRC, which is rotating around the European countries in September. And then the CICC, which is located in United States, mostly in the April timeframe. We also having the wide collaboration among the societies like IEEE CEDA, which is the EDA Council, and also the Sensors Council, and so on and so forth. Also, the several activities like IEEE Nano, IEEE Brain, and so on and so forth. We have several publications, which is the Journal of Solid-State Circuit, which is our flagship journal, by the way. And also we have the SSC letters, SSCS magazines, and also we started open journal of solid-state circuit. So, and also we have the very rich educational contents in the SSCS Resource Center. If you have a chance to look into there, we have the many tutorial, recorded videos among not only the ISCC but many other conferences, as well as we they monthly organize the SSCS webinars, and we also put those recorded videos there. So this is the membership benefit. So I highly recommend if you are going to be a specialist or professionals in this area, you join this and they're taking the full advantage of the resources. And also here, this is one of the 100 chapters worldwide, but the chapter having organizing this kind of the lecture series, also working for community services and many kinds of events. So please join such kind of events whenever they're existing. And also, in addition to that, we have the several special outreach activities like PICO Open Source Silicon Design Project, or in major conferences, we are doing circuit insights for undergraduate, doing one day the sort of tutorial type lectures. And of course, we started student circuit contests or Arduino design contest. And also, we initiated sort of the PCB design for high school students, mainly in the United States. But if you are interested in these kind of activities, please join that, as well as please start organizing this kind of things. The interaction among the experts in the worldwide will be very beneficial. So unfortunately, there are not yet having the major conferences in Latin America, I should say. But we are seeking of co-working with sort of the conferences like SSCS held in the Latin America areas, so that we have much better visibility to you. So please join us, or please take full advantage of being the SSCS membership. See some echoing, so if you can control that. But anyway, let's get back to my main talk. Please join us, or please take. Hopefully, situation will be solved. So I'm not quite sure that you already received my slide, and I will do that in my first part and take the questions and break after hopefully 1 hour, and continue for a bit added the topics, which is the hardware accelerator design for crypto algorithm. It's not necessarily only the crypto algorithm, but it's something like an algorithm to hardware design, or especially digital design. And also we have several activities for chip design and tape-out courses in our university, so I'd like to share that. I heard that you have just started the chip tape-out courses in this university, so that would be very good to exchange this kind of experiences. So let's get started. So this is the outline, but maybe I will take some 10 minutes break here and taking questions. So at first part, I'll talk about the very basics of asynchronous circuit designs. And they talk about the 2 very extreme cases of design examples. And then I'm going to show about measurement result. So basically, asynchronous circuit have been intensively studied for more than 40 years. Unfortunately, or I shouldn't say unfortunate, but although there are many the intensive research is existing, but still there have been less the industrial product existing utilizing the full asynchronous controlling. There are, of course, several reasons, but we need to seriously think about that. But anyway, the advantage that we are claiming for the utilizing asynchronous controlling is that if the technology advances, then the variation becomes a serious issue for, say, nanometer CMOS. I'll mention a bit later, but it is always mentioned about that, but it's not always true. For example, when we have been discussing about the sub 1000 nanometer process, many people are mentioning that the variation causes huge amount of the issues. But after introduction of the high-K metal gate after 65 and 40 nano, variation reduced drastically. So these kind of issues have been solved by the mega pub like TSMC and so on and so forth. Then what happened later on? So we introduced the FinFET in around 10 or the 15 years, firstly by Intel by 22 nano. And FinFET also drastically reducing the variation. So now the TSMC is producing the 3 nano as the latest technologies, and moving toward the 2 nano the manufacturing. Still, the variation is kept under control. So although we are claiming that for nanometer CMOS process or advanced process technology, variation becomes huge, but it's not really true for many cases. But anyway, on the other side, if you're talking about the very low voltage operation, like the to energy minimum operations, at that point variation is very serious, to be honest. So if you are seeking to establish IoT devices with very low power, low energy operations, somehow you need to cope with that kind of the situations. Of course, the recently, or at least more than the past 10 years, power consumption for entire chip is getting very, very the critical issue. And on top of that, the clock, the power consumption induced by clock network is getting bigger and bigger. And now almost the 1/3 of power is consumed by clock netlist. So avoiding such kind of the power consumption by clocking is also very important. And also, because I have been working for hardware security for past 10 to 15 years, clock information or synchronization signal is the disclosing the information inside process. So if you need to work with the security, we need to consider such kind of signals to the outside. So the asynchronous controlling have advantage that we are free from using global clocking. So power could be reduced. This kind of the signals, clock-related synchronous signal, could be eliminated. So this could be still the very important advantage using asynchronous controlling. So let me introduce some of the characteristics. So if you're talking about process variations, most people assume that the time delay changes according to the process, or chip to chip, or die to die, or wafer to wafer, or so on and so forth. But you have to be seriously think if the variation becomes large, because it's not necessarily only the macroscopic issues, but we need to seek into the very microscopic phenomena. For example, if you change the data or instruction in microprocessors, that changes the delay of the data path. For example, this is the case for the instructions and data changes. So for the case of logical operations, of course, the path delay is almost uniform. So there are no divide delay distribution existing. But for the case of the addition or subtraction, or maybe if you introduce the multiplications, delay changes according to your data. And that, of course, changes according to your operating temperature, your operating voltage. And the important thing is, if you're talking about worst case delay, which is very critical for your synchronous design, worst case delay changes drastically. So that means if you're working with the synchronous design and you need to comply with such variations, you have to very, very carefully analyze where will be the worst case delay if you change the temperature, if you change the voltage, or there existing process variations. So that means you have to put huge amount of the, margins for your designs. And that might not be practical if, especially going down to very low voltage or higher temperature or something. Of course, in addition to that, we are suffering from the noises, which might coming from the outside to your chip, or even your chip itself induces the noises, which causes your operation of the circuit itself. Also, the transistor is relatively tough against the aging, but still we are suffering from the aging issue like NPTI and so on and so forth. So if such kind of thing happens, then this kind of delay the distribution also changes. So again and again, if you're working with synchronous, then we have to cope with such kind of very big possibility of the delay variations. So that's the reason we are saying asynchronous might be very important. Although about 15 years ago, people mentioned that in year 2026, which should be next year, the delay, the uncertainty is up to about 40%. As I mentioned, it will not be true for the current forecast for the next year. Delay is still kept below 10% of the circuit, even you are using advanced process like 2 or 3 nanos. But again and again, if you're working with very low voltage operation, delay changes drastically, become larger. So depending on the situation, you have to seriously think about that. Then let me briefly talking about the asynchronous signaling. So basically, instead of the toggling flip-flop by global synchronous clocks in between logics, we use so-called handshaking in between the flip-flop among the logics. This means if we generate these kind of handshaking signals at the end of your logic, detecting the completion of the operation, that can guarantee wherever the variation existing, you can guarantee that the logic is completed. So this is the very important characteristics. I will talk in a bit detail about how to do that, but this is the basic idea of using asynchronous signaling. So because there are no clock existing, then at least the delay of, say, the data path even changes, the controlling itself is delay insensitive. And on top of that, because the toggling point of the controlling changes according to the delay of each blocks, like the delay time here or delay time here and so on and so forth. So there will be less the toggling oriented or clock oriented the spikes existing, than the having the great advantage for security measures. And in addition to that, there is or almost everyone working in a synchronous circuit is claiming that the operation can be averaged by the delay variation in each the portions. Instead, if you're working with synchronous circuit, then we need to cope with the worst case delay of the operations. So that having the another advantage in terms of performances. So let me go into a bit detail about how the people are working for asynchronous controlling. As I mentioned, ideally we need to have the completion detection at the end of the data path, something the data processing unit, and generating handshaking signal to the previous the logic, so that we can declare that this control unit is now open for next data. Or we can say that to the next stage that this processing unit is ready to send the data to the next stage. So this is handshaking. This is the fully asynchronous controlling, and that could be having a huge advantage, complying with the previously mentioned the advantages. But on the other side, this requires huge the completion detection circuit trees at the end of each the processing unit. So this causes huge amount of overhead in terms of performance, of course, circuit area, the power consumption, and so on and so forth. So usually people don't like this kind of the fully asynchronous controlling because of too much overhead. Instead, people are utilizing this kind of shared asynchronous controlling that putting, for some cases, the delay lines mimicking the logic unit. So that make it the handshaking control very easy. This having the huge advantage, having the less the controlling overhead, but you might be well aware that this is something like a shared or fake asynchronous controlling. So this, as I mentioned here, delay changing according to data, temperature, and operating voltage. So this delay line cannot completely mimicking the delay change according to such kind of variations. So for that, we need to put certain amount of margin for this delay line for the correct operation. This is almost identical to synchronous controlling. So there are less advantage compared with synchronous controlling and the shared asynchronous controlling. So of course, this is the choice. Whether you like the less controlling overhead, taking some advantage of the asynchronous controlling, or allowing the huge amount of controlling overhead with the fully the beneficial of the asynchronous controlling. So in my talk from now on, I'll use this fully asynchronous one because I don't like shared one, to be honest, because it's something like a faking. Anyway, so let me introduce the fun we have been doing. So before going to the detail, basically we are using this kind of dynamic the dual rail circuit, DCVSL in short, for controlling. Dynamic circuit having the advantage that during the one cycle of operation, the output, the transit only once, depending on the input. And in addition to that, because dual rail manners, either one of the output will transit, and the other portion remains as it is. So this means we have the pre-charging of the internal logic causes the 0, in output because we put the inverters here. If the operation is correctly done, then either of the output transit to 1. So with this, we can detect the completion of the operation of this logic by detecting 0, 1 or 1, 0 output. Of course, if something wrong happens, then both of the dynamic node discharges, causes the 1, 1. So sometimes we can utilize this as a logic error situation. So that is another advantage. But anyway, with detecting this 0, 1, 1, 0, we can autonomously detecting the completion of logic. I will skip this portion, but as I mentioned, if you are talking about the security, then this kind of balance operation without using the global clocking, there are less emission to the outside, so that even utilizing the differential power analysis, which is very commonly used for the side channels for security hardwares. The controlling exhibit no significant signal depending on the internal states. So this having the great advantage for such kind of applications as well. So from now, I would like to discuss about the two extreme cases of fully asynchronous controlling, which is the coarse-grained asynchronous controlling to minimize the controlling overhead. The other one is fine-grained asynchronous controlling, which are utilizing the gate-level asynchronous controlling, which might be some crazy idea, but I'll talk the advantage using that kind of controlling. Then I'll talk about the measurement result, not necessarily the performance itself, but as I mentioned at the beginning, asynchronous controlling have an advantage that having the immunity against the noises, or immunity against the variations, or average operations. So far until now, although many people are claiming about such kind of thing, but as far as I understand, in the asynchronous, the researching areas, nobody is really demonstrating that kind of things in real measurement. So I'll talk about that. This is the advantage utilizing the full asynchronous controlling, by the way. So the first, the extreme case is the very coarse-grained, the asynchronous controlling. Then I will talk about the architecture in the next slide, but we have designed the microprocessor by that controlling. By the way, at that time, we used 19 nano. And so we wanted to demonstrate the asynchronous controlling is correctly operating in the microprocessor level. And in addition to that, the free from utilizing the global clock. Maybe you might know that in the digital design, people are often using DCVSL or DVS, dynamic voltage scaling, for scaling the performance to reduce the power consumption. But the asynchronous control having the not practical to utilizing only the DVS control. So we would like to demonstrate even using the asynchronous control, we can do similar the controlling to minimize the power consumption or energy consumption. So we put in addition to the microprocessor, we put DC-DC converter on chip and autonomously controlling the operating voltage according to the required performance. And we demonstrated the operation. So as I mentioned, the architecture is very simple, but instead of utilizing pipeline architectures, we unload entire pipeline and make it only one clock cycle operations. You might assume that is the out-of-dated the architecture, but to make it simple, the controlling. And at the end of the instruction, before going back to the register or write back, we put the huge completion detection, the circuit. It is a complete completion detection circuit. So all the signals coming into the register is captured, and once everything is completed, we write back to the register and then continue to the next instructions. So this is very coarse-grained the controlling of the asynchronous signals. We put DC-DC converter to controlling that, and the detail is not so interesting, but this is very, very basic, band controlling DC-DC converters. But that should be good enough. The important thing is we put the counters to the monitor, how many the operations have been completed. Because completion can be easily detected by the completion signals. So we can just count the number of them. And if that is far above the requirement, then we can just reducing the operating voltage. If that is not so sufficient or higher performance is required, then we can just raise the operating voltage. Then the processing of processor can be autonomously controlled by the performance to realize the power optimum, the operations according to the performance requirement. So how we did that? We just counted the number of completion as I mentioned, and if the number of the instruction requires is say the higher than the target, which is 6 instructions in certain period, then we reduce the speed by reducing the operating voltage, or the opposite for the case that we require the speed up. And if the performance is the same, we keep the performance. So this is a measurement result of power supply voltage. We have some fluctuation because it autonomously done all the times. But anyway, this is the target number of the performance that we apply to the chip. Then the measured average performance is something like this, just following the target autonomously. We haven't done any the off-chip controlling on this, but the performance is adapted. Here you can see the overshooting of the result, so we have some adjustment, and we come down to the lower performance according to the performance requirement changes. So this is one example, but for this case, the completion detection, the circuit causes about 15 to 30% of the performance or the delay time, overhead of delay time, as well as power consumption, the number of gates. So it's very huge in our sense. Also, we have the advantage of using benefit of using this kind of feature. So instead, we try to do the very fine-grained asynchronous controlling. Because, as I mentioned, we basically using DCBSL, dual layer the dynamic circuit, as an element of the logic. So each logic having controlling the completion signals. So with that, if we can doing the handshaking in between the gates, we can do the much better controlling. And in addition to that, for the case of microprocessor, we have so many the controlling branches. And if you have learned something about asynchronous controlling, then if you have a signal, they split into several places, or if signal is coming into your gate, we need to put the so-called C element, which is the arbiter circuit. The arbiter circuit becomes too complicated if you have so many the split or fan out or fan ins. Instead, if you are working with logic level, do you know how many the fan out you usually use for your logic, or how many input for single the gate usually have? If you are using synopsis design compilers, it's not so often using 4 input logic gate. It's usually up to 3 input gates. For the case of the fan out, of course, except for the clock netlist, the fan out is also kept down to 3 to 4 for the case of especially the performance, the optimization. That means the C element can be minimized. The complexity of C element can be minimized. So that is the basic idea, to eliminate such kind of complexity in the controlling of handshaking. And I will show the circuit detail, but it requires huge amount of the controlling overhead. So how we can avoid that, or how we can avoid the concealing the overhead will be one of our interests. So instead of doing the random logic, we have applied that kind of controlling to FPGA designs. So, if some of you having the knowledge about the FPGA consists of lookup tables, which is a configurable logic, but most of the areas for lookup tables occupied by the SRAM or configuration memories. So even using the synchronous FPGA like Intel or Xilinx, their lookup table size is something like the 2 million lambda square. Maybe you learned lambda, the notation, in your digital logic design courses. Hopefully, this is sort of normalize the area, the notations. So instead, even with the huge amount of the controlling overhead, our design can keep into 2.2 to 2.7 million. So that means controlling overhead could be almost completely concealed by such kind of SRAM configuration memories. That was what we observed. But anyway, we want to demonstrate the advantage of the asynchronous controlling by the fine-grained handshaking. So we have utilizing the DCBSL as well for the completion detection. And I will mention about this later, but we employ sort of the dual pipeline architecture because dynamic circuit basically require the pre-charging phase and the evaluation phase. So many people are talking the evaluation, during the evaluation phase, the operation or delay for evaluation is shorter than the CMOS circuit. But it's not true because you need to think of the pre-charging phase. Otherwise, it's not fair comparison. So the question is how we can concealing the pre-charging time and how we can precisely control the pre-charging time is the very important aspect for the using DCBSL dynamic circuit. So this have been already mentioned, but if you're utilizing this kind of dynamic circuit, we need to have an evaluation which is very fast comparing with CMOS, and also the NMOS tree itself is smaller because we don't require the PMOS circuit. But if you consider with this kind of the foot transistor or pre-charging transistor and the output inverters, number of transistors becomes huge. For example, if you are simply designing 2-input NAND gate, you can use only 4 transistors for CMOS. But for this case, you have to use at least 2 transistors for NMOS 3, and 2 transistors for foot and the pre-charging and 2. So total amount of the gates the transistors are 6. If you are utilizing dual rail manner, then the number of transistors will go up to 10. So the overhead is something like 2.5x larger. Although we mentioned that the faster operation here, we need to have the pre-charging time required. So that is another overhead for controlling. So how we did that? We put the identical circuit here. We call N plane and the P plane. It doesn't matter N and P, but still, you might assume that it's so huge. For example, we need to add 10 more transistors and 2 more transistors. So it becomes 22 transistors for only NAND gate, comparing with 4 transistor CMOS. But for this, we can conceal the pre-charging because it's something flipping operation. So while this N portion is in evaluation operation mode, then P plane is in pre-charging mode. So the average performance per the entire block becomes double. And also, in addition to that, we don't require the pre-charging the timing control. And usually it is very important that the pre-charging is done by these PMOS transistors. So pre-charging time is much faster than this evaluation, the operation done by these NMOS, the pull-down networks. So with this, we can guarantee the correct operation of pre-charging. We don't require the pre-charging controlling. Of course, you assume that it is too big for only 2-input NAND gate. But this having another advantage. We can utilize the very simple completion detection circuit here. For the case of this, the simple DCBSL, the completion detection circuit, something like detecting 0, 1 or 1, 0, which means the exclusive or at least we need to utilize OR gate, which requires 4 transistors. For this case, we can only use we can utilize dynamic detection circuit, which is still in 4 transistors for both the circuitry. So this is another advantage. What else? So, of course, if you're talking about very small logic like a 2-input NAND gate, the overhead is too large. But if you're talking about such larger the logic like a 3-input lookup table or any kind of logic implementation having this kind of 3 structures, number of transistor overhead comparing with CMOS and this dynamic circuit becomes relatively small. And on top of that, for the case of lookup table, we need to have SRAM, the configuration memory, for each logics or each the branches. So SRAM, they dominate the areas. Because of that, the entire area overhead comparing with the CMOS lookup table becomes minimized, as I mentioned. And as I mentioned, the completion detection circuit could be very the simple one, so that they can be the very simple controlling. And to realize the lookup table, it's not only the lookup table, but also we require the configuration of network, configuration of the multiplexers that connect to the other lookup tables, and also we need to split the signal to the other lookup tables. As I mentioned at the beginning, we need to utilize the C element if we have such kind of multiplexing or the splitting the signal. So instead of putting the complicated C element in between the connection, we put that one inside the lookup table, and before going to the network, we use the copying circuit, which is just identical to the buffers, to make the controlling very simple. So the lookup table itself consists with 3-stage pipelining, and also the switching box or networking also consisting with the pipeline stages. So in total, you need to utilize several clocks among the lookup tables, but that makes the latency for each stage is minimized. If you want to go up to much larger lookup table, so recently many FPGA the providers like Intel or Xilinx using 5 to 6 input lookup tables. We could utilize this kind of decoded tree type the structures instead of simple this kind of tree structures. So this again requires one additional pipeline stages, but that is not so significant. So at the end, they require that kind of structure with 48-bit SRAMs as a configuration memory. As I mentioned earlier, this is a significant source of the area overhead for entire the logics. Of course, for the multiplexers, we put this kind of circuit, and sometimes we need to realize sort of token generators for asynchronous controlling or the signaling back to the other lookup tables, or asynchronous the switch box, just the buffers, and configuration memories, which is the SRAM with the multiple input, the bit line configurations. So in total, we use the 10 transistor SRAMs configurations. In addition to that, we need to connect the asynchronous FPGA to the outside, which is usually the synchronous circuit. So for that, we need to have the sort of the synchronization circuit in between. So we put this kind of the synchronization control, which convert data and the clock into asynchronous the signaling. And as I mentioned, because asynchronous portion operate according to the autonomous operations. So we need to fill all the data from the synchronous portion to the asynchronous or asynchronous portion to the synchronous. So for that, we need to put FIFO so that we can balancing the signaling in the synchronous domain and the asynchronous domains. Otherwise, sometimes we need to make the asynchronous controlling wait, or we might having the complicated controlling to the outside, let the synchronous circuit wait for your signals. So as I mentioned, we have several versions of the asynchronous FPGA designs. I'll talk the details, but in addition to such kind of functionality, we put some other the functions inside, which at the beginning is leakage controlling. So although if we go back to this basic circuit, dynamic circuit itself having the problem if you have a large leakage flowing, then dynamic node will be discharging even they should kept in the one level here. So of course, sometimes it is often true that we put the keeper circuit here, but instead, if we can control this the foot transistor as sort of power switching, you know, these days many people in synchronous or processors are utilizing power switching for turning off the blocks for minimizing the power consumption. We could utilize this kind of ideas for asynchronous controlling because we have the fully controlled signals coming from the current logic, previous logic, or next logic. That means if talking about the signals coming from the previous stage to current stage, before the completion of previous stage propagate to the gate, we don't require the turning off the gate because there are no signal existing. So we can turn off the foot transistors to minimize the leakage power. That should be true for the next stage. So with such kind of precisely controlling, without the huge amount of the controlling overhead, we could eliminate the leakage power induced by the non-operating period. This is very important when you operate this circuit in low voltage, slow operating conditions. That is the useless for the full speed operations, of course, but that could be very helpful for minimizing the power consumption for low power consumption. We call this gate level power gating. So the additional overhead for the controlling circuit is very minimized. And of course, we have some the controlling overhead existing, but we could proprietary reduce the power consumption. I will show that one later. And at the end, we also put utilizing error detection capability of the DC-based circuit, so that if the erroneous operation happening in each gate, we can stop operation and retry the same operation, either by raising the operating voltage, so that to minimize the error. To do that, of course, we need to detect the signals, as I mentioned, and also the other portion is keeping 0-0 eternally. So for that, we need to have sort of the watchdog circuit, which consists of delay, usually regarded as the good amount of time which the circuit should operate. So with this kind of the watchdog circuit, we can detect the erroneous operation, we can retry or doing something. So the result will be discussed later on. So anyway, this is the sort of the design portion of the asynchronous circuit. So it's about 1 hour. So I would like to take a break, but before that, if you have any question up to now for the design, the perspectives of the asynchronous controlling, I'm happy to take any kind of questions.
Sí.
Bueno, ahora vamos a abrir un espacio para las preguntas. No sé si alguno tenga preguntas o vía streaming también están recibiendo preguntas. La pueden hacer en español o en inglés. Y si la hacen en español, pues nosotros acá la podemos traducir. Entonces, no sé, levanten la mano si tienen alguna pregunta.
Okay. My question is related, well, you talk about the design at, well, let's say the schematic level. My question is more related to the physical design level, where when we are designing synchronous circuits with typical physical design tools, there's a phase called the clock-tree synthesis. Here, we don't have a clock, but we can still have timing issues. Is there any equivalent of the clock-tree synthesis from asynchronous circuits?
Basically, as I mentioned, asynchronous controlling delay insensitive design. If that is true for if the handshaking is completed. But before going to the handshaking or before designing the circuit itself, that is very critical delay sensitive design. And unfortunately, none of the design automation tool can be available at this moment. So basically, we design from the scratch by hand, just like analog design, and doing the careful timing analysis on that. Of course, timing analysis is just for this portion. So we need to carefully check the completion signal is proprietary generated, or as I mentioned, this operation is proprietary done in wide range of operating voltage, and so on and so forth. But again, there are no automated tool existing. I will talk that kind of thing later part for the realizing random logic by this controlling, but it is not still well working. So that's the very important portion. Of course, many asynchronous designers doing the researches that can mimicking the say the current the automated design tool. For example, for this case, if you carefully design this delay line for each processing unit, then after that you can almost automated using automated design tools and attaching delay line and this control logic. In addition, not by the design automation, by say the modifying your netlist. And of course, at the end for the present route, we can again back to the automated present route if we have the dedicated cell libraries for this kind of circuit. That's what is the currently people are doing.
¿Alguno tiene otra pregunta?
Excuse me, what industry applications are there?
Unfortunately, as I mentioned at the beginning, there are no industry application widely utilizing the asynchronous controlling existing, unfortunately. Of course, there are some niche applications existing, but that is the current situation. The reason is, as I mentioned here, although people are claiming a huge amount of uncertainty or delay variation might be expected, but it's not true. So still synchronous design with carefully the timing analysis would be much easier to design, verify, and they apply into the real product instead of using asynchronous controlling. That is the current situation, unfortunately. But in very niche application like the security, the hardware, for example, they require the very low emission to the outside. For that, they are somehow mimicking this kind of asynchronous controlling by using double DDL or something. So that is current situation, unfortunately. So in the industrial perspective, it's still far away from the industrialization. Yes, so we can take 5 minutes break and we resume 10 and 9:15.
Ahora vamos a tener un pequeño coffee break y continuamos a las 9:15. Entonces, por si quieren salir un rato, tomar café.
Aún no hay café.
Bueno, vamos a continuar con la charla.
So let's get started. For coming maybe 15 minutes, I will discuss about the measurement results that I. But okay, that's fine. I wait. So maybe we will start in 2 minutes or something. Sorry. Okay, so let's get started. So the measurement performance itself is not so I should say important, but the just the measurement result. But anyway, if you are talking about the coarse grain FPGA designs, because the each stages correspond to very small logics. So because of that, the performance is going up to almost 2.6 gigahertz to 3 gigahertz. Sometimes we need to have the overhead for the power-gated version, but that is the performance. So even using 65 nano process, at that time, I think the Intel microprocessor they exhibit only about 1 gigahertz operation or something. So in such sense, the operating frequency is very high. And on top of that, if you are working with synchronous design with, say, 3 gigahertz operations, you need to have very, very precise timing control. And sometimes you might need to have PLL from outside to control everything. That is annoying for you, maybe, or even to me. But for this is autonomously done. That means we don't need to have PLL. We don't need to have any precise timing control in coarse grain, as having the question in the first part that what is the timing issue? We need to be carefully design the logic itself, but the controlling itself, we don't have any the controlling the required for such high operating frequency. On top of that, as I expected or as we intended, even we lower the operating voltage down to say 300 millivolt, it operates. And we can easily extract the energy minimum point, even with very wide timing variation showing here. Well, it may be boring at this moment, but important thing is, for example, I mentioned that we introduced the gate level power gating for slow operations. This is very effective. For example, if we operate 1.2 volt with very low operating frequency, usually it operates up to say 1 gigahertz, but we operate down to 50 megahertz or 500 kilohertz. Then, because the leakage components become larger, but we could easily eliminate such kind of leakage component. So the energy of the consumption per one cycle is drastically reduced down to 1/50. Or even in the lower operating voltage, that the tendency continues. So for this case, this kind of the gate level power gating is very effective for slower operations in low voltage operation or the load conditions. Well, I'll skip this portion, but we could realize the performance up to 3 gigahertz operation in individual logics. And if we fairly compare with the other competing the asynchronous controlling FPGAs, this one having almost identical structures, but only difference is they didn't use the dual planes, as I mentioned, to concealing the pre-charging time. So their performance is only half, even utilizing the same 65 nano process. So this is the clear advantage using the such dual plane operations. Of course, if we add the power gating, the performance degrades to some extent. If we they introduce error detection, the performance degrades to some extent. But there have the advantage. I will talk about it later. Anyway, even fairly comparing with the commercially available FPGA with the 65 nano generations, the individual operations could be the performance per individual operation or energy consumption per individual operation can be drastically reduced, like 3 times to 5 times. So this is a clear advantage, free from clock, eliminating the leakage and so on and so forth. But the important portion is from now on. So as I mentioned, the asynchronous controlling have an advantage of the average operation, noise immunity, and so on and so forth. But nobody in the past having demonstrated that kind of things in real measurement. So what we expect is that for the synchronous operation, if the introduced noise become larger, from time to time you will fail the operation by the delay time increase or something. So the error rate is increasing in proportion to the noise, and at the end they will cease by operation or stop operations or malfunction. For the case of the asynchronous controlling, we expect that if the noise amplitude is going to some extent, there will be error-free operation demonstrated, then at the end, they will malfunction suddenly. That is what people are expecting, or even I myself is expecting. So we have demonstrated several trials. One is for the case of microprocessor I talked at the beginning. This is the asynchronous microprocessors. This is synchronous, the same architecture microprocessor. And we put noise sources surrounding these CPUs. And the noise is something like a random noise. And the amount of noise can be increased or decreased by the activating these noise sources. So, we have measured the synchronous CPUs while increasing the noise amount. Then, as I expected, error rate increases according to the noise. That is just expected. So it's no the surprise. For the case of asynchronous operations, it's a bit curious, but if increasing the noise to the same amount as the synchronous microprocessors, it operates as I expected, the 100% free from noises, the errors, but delay or performance degrades to some extent like this. So for the case of microprocessors, the noises causes sort of the delay increase, average delay increase, instead of the error increase. That is because for this case, noise is something just like the IR dropping. So IR dropping means the average operating voltage is dropped some amount. So that means the average operation is dropped, like showing here. So this is again and again not surprising. So, but still, important thing is nobody else having ever reported this kind of phenomenon. So this is one thing, very important characteristic that have been discussed for the advantage of asynchronous controlling. Again and again, I should say that there are no free from errors up to this amount of noises. I don't know how much noises in reality for this case, but this is significant noise. Then we tried using the FPGA, asynchronous FPGA design for further investigation of noise in terms of injecting the noise from outside or the introduced noise. So for the case of injecting noises, we use sinusoidal the noises from outside. This is important. It's not just the dropping noise, but it's something like a sinusoidal in the operating voltage conditions. So what happened for the real measurement? This is a measurement result according to the change of the noise amplitude introduced from outside, then according to the noise frequency and the performance. So as I mentioned, performance somehow degraded introducing the noises in the IR drop case. For this case, this is sinusoidal noises. I'm so surprised seeing this measurement result. Well, actually, I discussed with my student, and I let him measure once again because it's so surprising. Because for here, even introducing noises, there's no performance degradation observed. So I suspect this is something like the artifact of the student measurement. But after trying many times, he always demonstrated this measurement result. And we came to conclude that this is reality. Why? This is something clearly showing the average operation. So this is the FPGA with logic chains. we introduced the sinusoidal noises. But so some time if the noise is dropping portion, the logic is affected to a slower operation. But if the noise go up above the VDD, it speed up. At the end, they are average. So these portions clearly demonstrate that phenomenon. This is really measurement results. So we are so surprised with that. And there's some drop of performance. Can you recognize what is happening here? Here or there, or here? These are different configurations of FPGA, by the way. Again and again, we discussed what is happening, and at the end, we come to conclude that this portion is something like a harmonious, the operating frequency of the logic. So if the noises and operation is somehow synchronized, then that continuously they affected by the lower operating condition or something. So this clearly shows this one. So this is I don't know the main operating the frequency of that logic. This is something like the second harmonics and so on and so forth. If you and then because of that we change the configuration to change the operating speed of the logic, and it clearly shows that the harmonic, the frequency changes. So again and again, this is very surprising result, demonstrating the average operation of asynchronous controlling for entire data path. Then we also carried out the sort of internally induced noise according to the performance. So this is the expected performance for the ripple carrier ADAS inside the FPGAs. But if you increase the number of logic operating, the performance degrades almost linearly according to the number of logic. This is because the operation itself is something like synchronous to the main operation itself. So it always causes this kind of the locking phenomena for the noises induced by the circuit itself. So this is clearly showing that the performance is affected by the noises, but at the same time performance can be kept in average if the noise component is outside of the operating frequency. So we tried the configuration, then they come to conclude that if we have a internal noise existing and introduced noise existing, the performance degradation is something like this. So we have internal noise component existing, then the introduced noise component existing for the performance degradation for asynchronous FPGAs controlling. Of course, this can be applied for the aging. So we tried this kind of aging testing, and the performance is degraded, something like that, before malfunction. Until this point, there are no error existing for the entire operation, but at the end, this malfunctioned. So this they gives us that if we see the performance degradation to some extent, we can decide this is something like the affected by aging, so that it will be the time for replacing your chip. So this could be also regarded as autonomous the aging monitoring. How about noise detection? As I mentioned, we put noise detection circuit inside for the one version, and we tried introducing huge amount of noises from the outside. Of course, if the power supply is 400 millivolt, the noises causes the stop operation for the case of the 200 millivolt peak to peak. If we increase the power supply voltage up to 800 millivolt, it's stop operation with a noise of 650 millivolt peak to peak. Surprisingly, if we go up to 1.2 volt operations, it's stop operation for even up to 1 volt peak to peak noises without any errors are propagating to the next stage, because each logic can detect the noises, the errors. So this is the amount of error we counted, but they still, because of the error correction capability, we can realize the error-free operations. So we summarize it like this. So without any error detection circuitry, the error immunity is something like this. But the error immunity improved something like this, so 30% improvement or 25% improvement by putting the error detection circuit inside. Of course, this is with some amount of the performance overhead, area overhead. But that is also very beneficial if you need to operate this kind of circuit in very the tough environment. So, as I mentioned, to answering your questions, so we wanted to apply this one to the random logic, but until now it's not so successfully done. So, what we tried is that just like digital circuit design, we introduced RTL and doing the logic synthesis by design compiler. And at that time, we used a very simple script to translate the netlist to the the circuit. Introducing completion detection circuit and signaling. And with the proper cell libraries for those dual circuits, we could do the place and route for obtaining a layout, and the chip could be fabricated properly. And timing for this portion is not so important, because the timing can be guaranteed by the handshaking. So all the important portion is the cell design of the dual logic cells. But the problem is that this is something like a logic level synchronization. So if you are working with pipelining, you have to synchronize the pipeline stages for all the times. This should be true for logic level. So if you have logic trees, all the logic elements should be aligned in pipeline manner. That means if you have any circuit that connecting directly to this and having the logic like this, we need to align all the data. That means we need to put pipeline element, that is the buffer here, to cope with that issue. So if we do that kind of thing, somehow the exhausting manner, then the amount of buffer is something like 80% of the entire logic. That means 5 times increase of the logic elements. So that is nothing useful. So of course, if we carefully observe the circuit itself, some of the buffer could be replaced to the logic, or we can precisely control the design compiler that they align entire logic depth. Then we could minimize such kind of the pipeline alignment, but still we require maybe the 50% of the entire logic for the pipeline alignment. So we are thinking it's still not so efficient at this moment, but still we are still working towards that, and especially if you're working for structured the element like the adders or multiplier or something, then this kind of thing could be very efficient. So that's what we are doing. So this is a brief summary of the asynchronous portion, including the measurement. So if you have any questions so far for measurement portion, I'm happy to take any questions. Oh, okay, yes.
I have a question. Actually, it was for the previous section, but I was wondering which applications do you think that the asynchronous circuits could have, not in the industry today, but in the future? You know, in some kind of areas like the medicine or some kind of devices, you know, that make devices that are more reliable and maybe more durable. Do you think that that is possible? And if it's so, in which kind of areas do you think that it will work?
Maybe you are very fresh, the younger generation, so your how to say, the bright idea could help. But anyway, that is joking. But that is a very important question. So as I mentioned, so far at this moment, there are very niche applications existing. One of which could be something like a neural networking. So as the people working for, say, AIs or something, and some of them are mimicking the brain for doing much the advanced processing, not like a LLM or something. So for that, they are introducing sort of neuron type the processing, and brain is something like asynchronous controlling. If we have the neuron fires, then that is propagating to the next neurons. That is the completely asynchronous manner. So if you are going to mimic such kind of neuron behavior, then asynchronous controlling would be one of the very promising direction. but anyway, so far, as I mentioned, here in measurement, if you are going to apply this one for very, very, say the environment that hard the situation, like application in the space, or apply to, say, the nuclear power plant or something, then this kind of tolerance would help. Of course, if you're talking about space, then they are discussing about reliability of operation itself or reliability of verification and so on and so forth, and that cannot currently comply in the asynchronous controlling. But still, that kind of thing could be very possible, because for the case of space application, at least to guarantee the reliability, they put triple the parallel operation for reliability, or for some cases 5 times parallel implementation. That means the area becomes 5 times larger, which is almost compatible with our design. Or our design is much smaller in some sense. So, and we have a capability of error detection, so we have some advantage. Error detection can be also applied for, say, the single event upset by the particles and so on and so forth. So that could be possible, but still, I'm still struggling the application. So. Okay.
Hey, good morning. My question is related to the control of the voltage. I mean, when you're implementing the dynamic voltage scaling, do you include this voltage control in a control loop, or how these changes are being made?
What we usually doing is that we have a careful the measurement by the logic testers individually, and making the tables for the operating voltage and the frequencies, and tuning the operating voltage like Intel speed step or something. But for this case, we can just simply drop the operating voltage. That's it. Of course, if that will not comply with your performance requirement, we can raise the operating voltage. And the first example we demonstrated is something doing that kind of thing autonomously. So asynchronous controlling, we don't require the controlling level timing issues. The controlling level is timing insensitive. So we can change the operating voltage as you like to change the performance. So that is what I demonstrated.
Good morning. My question is, when you add a watchdog to a gate level error detection, doesn't adding the watchdog add more gate delay? And if so, how do we guarantee that it doesn't affect error detection?
So, basically, this is not detecting entire errors, but it's just detecting the portion of errors can cause especially for dynamic circuit. If you're talking about error detection for ordinary CMOS circuit, most of the error sources is something like the flipping of data by some noises, by voltage or the particles, whatever. And most of the cases, because CMOS having the power to recover the data, except for flip-flop. So that's the reason many people are talking about the single event upset, which they flip the flip-flop, the data of flip-flop itself. So that is a problem for synchronous circuit. And of course, if such single event existing, delay changes, that causes the errors. That's a problem. For this case, for the dynamic circuit, such kind of event or noises causes some of the erroneous operation in dynamic circuit, which is the both of the network, the erroneously they pulled down. That we can detect the sort of 1-1 errors. Of course, the opposite things might also happen that we need to pull down the logic. But this is dynamic operation. So once the signal is has gone, then the dynamic circuit cannot pull down. Then that causes 0-0 error. So we need to wait until some portion of enough timing for detecting such kind of errors. So that's the reason we need to have watchdog at the same time. So this is at least the two major causes of the errors for the dynamic circuit. And well, of course, there could be some other error could be introduced to the completion detection circuit, which could be somewhere here. This is again the dynamic circuit node. So we might need to have some sort of error detection for this portion, or error recovery the operation for this one. But still, that is not yet done by ourselves. But those are the error causes. And other than that, because even having the delay increase, that could be solved autonomously by the handshaking. So that is what we are assuming for error detection for this asynchronous controlling. Is that answer to your question? Oh, yes.
Hello and good morning. I have a question around the difference in between the synchronous and asynchronous circuits, but you say that, or you show one trade-off between these circuits when there is noise. Is synchronous circuits have higher error than the asynchronous circuits, right?
But for the case of asynchronous controlling, even we introduce the noises or the voltage changes, because the handshaking guarantees the correct operation. So that's the reason we don't have any error increase at certain point. But of course, just like this. But of course, that increases the delay. That is shown here in these two figures. This is again the measurement result. So this means the synchronous increasing the noises, the errors. This asynchronous controlling increasing the delay time.
Asynchronous increase delay, right? Okay. When we as engineers have to select which circuit use, okay, when we have to use a synchronous or asynchronous circuit when we want more delay or less error.
That is again the design policy. So, of course, I'm working in synchronous design as well. So, if you need to cope with this kind of noise induced errors, one thing we can do is decreasing the operating frequency. Just the same as the asynchronous controlling that is autonomously doing. But nobody knows how much noise is introduced for the case of the synchronous circuit. Of course, if you put the noise detectors, you can somehow estimate that, and we can autonomously controlling the operating voltage. Well, if I have a time, I will introduce that one for the security portion. That have been always doing such kind of things. For the case of if I was a asynchronous the designers, if the noise is very huge or very predictable, then although I mentioned the reducing the operating frequency, but that causes a huge amount of the margins of operations, and sometimes it might not be practical. Then doing the asynchronous controlling could be helpful, but of course that is still having some difficulty of the designing. So I'm not quite sure this is only the solution, but still that is the part I have in my mind, which to choose according to the noise.
Bueno, ya no tenemos tiempo para más preguntas, ya vamos a hacer el cierre para pasar al coffee break que tenemos, y a las 10:10 más o menos empezaría la segunda charla.
Maybe I can say few more things because of the time. Yeah, I know. So with 4 more minutes. Well, so I have been working for hardware the security, but this is the part I mentioned. So there have been some default injection attacking that causes the erroneous operation for the security chip to extracting the behavior or inside the keys, secret keys. For that, we put sort of delay detection circuit, and if once the delay, the abnormally changes, then we stop operation or something. So that kind of thing is very essential. If you're working with synchronous to prevent such kind of erroneous operations. So that is already implemented. So that's the reason I'm saying that if you are working with synchronous, then this kind of thing could be very possible. So anyway, because of the time, I cannot go into the detail about how the design for digital portion, and also there are something we have been doing for the design the chip, the tapered courses that we have recently introduced. We have introduced this kind of 0.5-inch wafer manufacturing process here, located in the office, and can be doing the metal process for only 30 minutes. So we can do the taping out, and after 30 minutes, you can obtain the chip. So that is what we are doing now, and we want to introduce this kind of thing to the order of lectures as well in the near future. So that's what I'm doing. So I'm sending this kind of slide to you. So if you have any question further for the portion that I haven't have time to present, please let me know, and we can discuss later on. So thank you very much for your kind attention, and very
Thank you, Professor Makoto. As I mentioned, this is an initiative led by students, so I think that I can speak for all of us that it's something very motivational for all the students from all the levels, and even the professors, and to have you here bringing us these novel techniques, this knowledge. So I want to thank you for every single person here, and bueno, ahora vamos a pasar al coffee break, ahora sí, y luego tenemos la segunda charla a las 10:10. Entonces, ¿qué?
estamos separados, pero esperemos la de 15.
Buenos días, vamos a proseguir con la segunda charla. A continuación les voy a comentar un poco acerca de la biografía del doctor Cristian Durán. Cristian Durán nació en 1991 y obtuvo su título de ingeniero electrónico en la Universidad Industrial de Santander en 2014, su maestría en telecomunicaciones en 2017 y su doctorado en ingeniería electrónica en 2022. Entre 2019 y 2022 fue asistente de investigación en la Universidad de Electrocomunicaciones en Tokio, Japón, y actualmente es asistente de investigación en la Universidad de Tokio. Sus intereses de investigación incluyen arquitectura de computadores, redes neuronales y automatización del diseño electrónico. Por favor, denle una bienvenida al profesor.
Konnichiwa, minasan. No voy a hacer eso. Estaba pensando en hacerlo, pero no vale la pena. Muy feliz de volver. Ya han sido 6 años desde que me fui. Veo muchas caras nuevas. Estoy feliz de que mucha gente se encuentre bastante interesada en este rama de investigación de microelectrónica. Al fin y al cabo, si nosotros hablamos de semiconductores, prácticamente todo está hecho de semiconductores. Es bastante esencial para lo que nosotros manejamos en todas las áreas de tecnología hasta el momento. No hay cosa que no se haga con transistores, sin transistores. Fue prácticamente la última invención de la humanidad. Ustedes saben qué tan importante es y ya saben cuánta plata mueve. Entonces yo pienso que eso no hay necesidad de introducirlo. Pero sí me voy a introducir yo mismo. Yo soy Cristian Durán, así como dijeron, yo estoy de asistente en la Universidad de Tokio. Actualmente pertenezco al System Design Lab, que es lo que está el profesor Ikeda y Izuka. Pues nada, nosotros vamos a comenzar ya. Y no funciona. Y es por esto que nosotros necesitamos fabricar este tipo de cosas, ¿no? Al menos si nosotros pudiéramos fabricarlo, nosotros podríamos saber qué es lo que está pasando con eso, por qué no se mueve. Bueno, comencemos con AI. Ustedes están muy interesados en AI y les voy a dar una pequeña introducción de eso, pero yo pienso que ya en sus vidas está bastante integrada, por así decirlo. Entonces ya ustedes conocen todos esos modelos que le acaban de ver. El más popular de todos, que es el último que se ha hecho, es el LLM. Prácticamente es como todas las AIs que han visto hasta ahora. Es un montón de parámetros que hacen los cálculos y dependiendo de la interpretación de los cálculos que se haga, esto colocan, en este caso hacen tokenización. Y esto se retroalimenta para poder sacar las frases que hagan con respecto a la pregunta que ustedes hagan. Ha sido como la última, pero entonces si estamos hablando del escalamiento que va a tener inteligencia artificial en los últimos años, pues se va a disparar y porque requiere un montón de parámetros y requiere muchísimo más si queremos apuntar a, no sé, a lo que sea que se imagine la gente con respecto a AI, que es todo lo que sea completamente automatizado. Porque al fin y al cabo, este tipo de modelo no es más sino una superposición de muchas funciones lineales con billones de parámetros. Entonces, para poder hacer algo que está proyectando precisamente la industria, se estima de que más o menos, por lo menos estos gráficos de potencia, cada request estaría gastando 8 vatios por hora. Eso es inmenso. Si ustedes se dan cuenta, o sea, todas las personas están utilizando aquí ChatGPT y pues lo utilizan para cualquier cosa. Entonces, multiplique eso por billones y entonces usted se da cuenta de que ni siquiera alcanzamos para sacar todo eso. Y sí, hay crisis energética por este tipo de cosas. Pero entonces la idea es hacer un poquito de neuromorphic. Eso significa de que tratamos de imitar el cerebro humano lo mejor posible, pues para tener mejor eficiencia o para tener mejor resultado, cualquier tipo de cosa que hagan ahí. Entonces, prácticamente lo que estamos haciendo es coger el comportamiento de la neurona, la biológica, la que nosotros tenemos siempre, estudiar su funcionamiento y tratar de imitarlo, lo mismo que hemos hecho durante millones de años. Pero entonces vamos antes de ir a esa historia, les voy a compartir un poquito mi experiencia con ChatGPT, ¿no? Porque pues todo el mundo ahora está haciendo programación en ChatGPT y pues piensa que es la varita mágica que hace todo. Entonces usted le pregunta qué es lo que quiero que me haga esto en Python, quiero que me haga esto en C++, quiero que me haga esto en Verilog. Y lo que ustedes se van a dar cuenta es que apesta. Pero miren, aquí tengo este request que yo hice, que necesito hacer un SPI controller. Literalmente lo necesitaba para poder hacer el último tapeout, literalmente hace 3 semanas. Entonces, necesitaba un SPI rápido. Yo sé que tengo muchos prototipos por ahí, pero quería algo que simplemente otras personas pudieran utilizar y que supieran cómo hiciera así desde cero. Y pues decidí darle la oportunidad a ChatGPT porque literal me lo tiene en un minuto. Y me da un código, pero entonces yo miro en detalle cómo es que lo implementa y de una vez comienzan las ilegalidades. Si ustedes han estudiado bien su curso de digitales, ustedes se dan cuenta de que en RTL ustedes no pueden colocar dos listas de sensibilidad en dos diferentes always. Eso siempre va a ser ilegal y pues la razón por la que es ilegal es porque no existe físicamente un free flow que pueda dispararse 2 veces. O sea, uno que se dispare con un clock o con el otro clock. Y si lo intenta hacer, va a ser un ahorro, alguna cosa ahí rara, y cada ahorro va a colocar algún tipo de glitch o algo similar que simplemente no va a hacer funcionar. Esto no va a funcionar. Y ChatGPT no lo sabe. Y la razón por la que no lo sabe es porque ChatGPT no ha sido entrenado con este tipo de nuance. ¿Qué pasó? Ok. No lo ha hecho. Esta es otra cosa que intenté también hacer con respecto a intentar integrar circuitos integrados utilizando nuevas herramientas. Ustedes se dan cuenta que cuando están utilizando nuevas herramientas, lamentablemente la documentación no existe. Y usted se va a encontrar ese problema todo el tiempo. ¿Por qué es así, hermano? Es plata. La gente que hace este software, así como hace cualquier software, quieren vivir de la documentación, quieren vivir de todo lo que es soporte. El software en sí mismo no da la plata, la suscripción es lo que da la plata todo el tiempo. Entonces, todo lo que sea con respecto a documentación prácticamente no existe. Espérame un poquitico a ver que se cuadre, ¿no? Es un poquito distrayente. Listo. Déjelo así, eso leen. Y si no, miran el YouTube. Entonces yo estaba tratando de mirar a ver cómo hacer esto, cómo hago hacer anotaciones de SDF. Son importantes para hacer delays. Ustedes nunca han hecho una simulación post layout o post síntesis de un circuito que tiene que meterle los delays. ¿Cómo usted hace para meterle delays a las cosas que ya están sintetizadas? Eso se hace con un SDF, es un estándar y se supone que la herramienta me tiene que dar una forma de colocar el SDF. Y lo que me dice literalmente es, bueno, si lo quiero hacer en Node, simplemente cargue el SDC y haga el STA. Y yo como que, ¿y el resto? O sea, necesito cargar las librerías, necesito hacer place and route, necesito hacer el clock síntesis, necesito hacer todo eso y pues el ChatGPT no me dio nada. No, es que no existe. Y esto no ha sido entrenado, este tipo de cosas son demasiado secretivas. O sea, sí, está muy herméticamente cerrado e incluso entre universidades es así. No, por más de que haya colaboración, las colaboraciones no se hacen más sino pasarle el mismo código que ha hecho un man por allá como hace 10 años. Lo único que hacen es mejorarlo a partir de eso. Entonces, no ha sido entrenado con AI y AI no tiene ese tipo de experticia. Entonces, ese es mi punto. Ustedes no pueden ganar experticia utilizando inteligencia artificial. La inteligencia artificial no es más sino una herramienta más, y ese es mi punto de toda la charla. Y como toda herramienta, estamos hablando de Vivado, por ejemplo, es otra herramienta. Si estamos hablando de MATLAB, es otra herramienta. Si estamos hablando de Python, es otra herramienta. Toda herramienta simplemente se usa para su uso específico y ya. En mi caso, lo único que hago es esto, que me dé un código dummy para hacer algo y a partir de ahí es modificar. Es como lo más rápido, pero lo único que hago es optimizar lo que yo ya había hecho durante no sé cuánto tiempo. Este gráfico me gusta bastante. Yo lo creé hace ya 3 años. Tratando de ilustrar el problema que nosotros tenemos con código propietario y código libre. Todas tienen sus ventajas y sus desventajas. No piensen que porque es código libre y es gratis, esto puede hacer mejores cosas o lo puede modificar. No, ustedes ni siquiera saben cómo funciona. Y en el caso de closed source, pues no hay nada que ustedes se puedan apoyar. Les toca es con respecto a que alguien le enseñe, que venga de esos lugares y le enseñe a usted cómo utilizar esas herramientas. De resto no sabe cómo hacerlo, lo único que está haciendo es adivinar. Entonces, sí. Si estamos hablando de la parte de arriba, pues todo se encuentra secretivo, pero pues esto es que pues literalmente tiene una inversión muy grande. Eso es lo que mueve la plata, pues nada que hacer. Si ustedes lo hacen libre, pues pueden tener todo completamente hecho, pero no está verificado para nada. Y hacer las cosas abiertas, pues es simplemente pues botar prácticamente el trabajo, porque pues eso queda abierto y no gana nada, no gana migajas. Entonces pero pues puede modificar todo eso, pero les toca estudiar cómo es que funciona eso internamente, no es algo que se pueda usar. Entonces, si se va a usar herramientas libres, las pueden usar para hacer su hobby, pero usted quiere algo profesional, le toca la parte de arriba. Y entonces eso es lo que yo quiero decir acá, ¿no? No discriminen las herramientas, no pueden hacerlo. Pero entonces volvamos a AI. Con esa dicotomía que acabamos de ver con respecto de closed source y open source, no importa qué es lo que usted haga, si estamos enfocando todo a AI, la idea es enfocarse en 2 tipos de cosas. La una es automatizar circuitos, o hacer generación o verificación, que es una de las partes que yo he estado pues trabajando durante bastante tiempo. La otra es simplemente hacer aceleración de AI, que es otra de las cosas que estamos haciendo. Entonces, cada una tiene sus ventajas, sus desventajas. Si ustedes quieren generar circuitos, o sea que literalmente lo que están haciendo en este momento con ChatGPT, que ustedes meten un prompt y quieren que les bote el chip, no existe. Pero si quieren ir para allá, la idea es que pueden tener un diseño en horas o quizás minutos. Ojalá pudiéramos hacer chips como si nada. No existe. Y creo que el paradigma es que no va a existir. Muchos especulan eso en este momento, porque pues es demasiado complicado y ustedes entienden lo complicado que es en el momento que ustedes intentan hacer circuitos. Pero si ustedes intentan optimizar procesos utilizando la inteligencia artificial, pequeños procesos, yo les voy a dar algunos ejemplos. Se pueden dar cuenta de que esto puede resolver muchos de sus problemas que pueden hacer en el momento de diseñar circuitos. La otra historia es simplemente optimizar los algoritmos que ya se tienen para poder hacer mejores aceleradores. Lo bueno de eso es que si ustedes quieren plata, ahí está. Todo el mundo, especialmente Nvidia. Nvidia es el que más está botando plata en eso. Le sigue Facebook. Y la idea es que si ustedes hacen cualquier tipo de acelerador, si ustedes hacen cualquier tipo de acelerador, lo someten a, no sé, ISCAS y SSCS, los que estamos promocionando en ese momento, inmediatamente queda aceptado. Eso estoy diciendo en este momento. O sea, yo veo qué es lo que hay allá y es eso. Entonces esto, si quieren encaminarlo allá y de una vez esto, hacer un nombre por ustedes, pues lo pueden hacer allá también. Entonces, depende de cómo ustedes lo quieran atacar. Voy a comenzar un poquito hablando de la automatización de circuitos integrados. Siempre el problema que quiero resolver es el de siempre, ¿no? Los costos de diseño se disparan a cada rato y es exponencial. Lo que está pasando es la escala del transistor, la famosa ley de se me olvidó. Bueno, esa, gracias. El Moore dice que cada 10 años se va a duplicar, ¿sí? Entonces va a ser exponencial. Ya estamos llegando al límite. Hay muchas especulaciones que dicen que ya es el tamaño del transistor para la SRAM, que es el más crítico de todos, ya no se puede hacer más pequeño. O sea, entonces se están tratando de optimizar por otros lados para poder mantener la ley de Moore hasta donde se pueda. Porque en el momento en que la ley de Moore se pierda, ya no se puede aplicar. Entonces ya especulan de que este campo ya no va a prosperar. Bastante grave, ¿no? Entonces, por eso es que a cada rato intentan duplicar de todo eso. El problema es que eso crea un side effect, que es este que están viendo acá. Cada vez que se reduce el tamaño del transistor, el esfuerzo para poder hacer el circuito que quiere hacer con todo y su verificación y que salga el producto como tal, también se duplica. Y ustedes lo están viendo ahí, o sea, no es posible y cada vez requiere muchas más personas, mucha más gente, y no hay forma como de keep up, porque no existen suficientes diseñadores, solamente tenemos los suficientes, o sea, apenas están ustedes, por ejemplo, y si todos van por ejemplo, una empresa apenas si cubre el 1% de todo, entonces no es posible. Entonces, la idea es automatizar. Les voy a dar algunos ejemplos de los que he hecho durante mi estadía aquí en la Universidad de Santander y también en la Universidad de Tokio. Esto ha sido pues una continuación de lo que ya he hecho desde 2017. Esto que es intentar hacerse automatización de standard cells. ¿Por qué necesitamos standard cells? Porque es la unidad básica digital que ustedes tienen, una NOR, una NAND. Un flip-flop. Si ustedes quieren optimizar para cualquier tipo de sabor o cualquier tipo de utilidad que requieran, que se quiera optimizar para potencia, optimizar para timing, que sea más rápido, lo que sea, cada diseño es diferente. Entonces se requiere uno de esos. Uno por un lado. Yo enfoqué esto más fue a seguridad. Ustedes se dan cuenta aquí en esta parte de abajo de acá. Cada estándar cell tiene diferentes layouts, pese a ser el mismo circuito. Entonces esto sirve mucho para poder hacer ofuscación. Usted simplemente coge los diferentes layouts de un circuito, los mezcla en su flow de Pleasant Route y de repente usted no los puede, ya no los puede reconocer tan rápido. Ustedes lo pueden ver acá. Cuando nosotros estamos haciendo ya la verde es que significa que sí lo pudo detectar y lo rojo es que no lo pudo detectar. El circuito ya se encuentra ofuscado con las 4 celdas que se encuentran acá. Entonces, ustedes intentan atacar con el conocimiento que tienen de las standard cells, lo que tienen normal, con solamente un nivel y no es capaz, simplemente no es capaz de extraer el circuito. Ya con 2 niveles o 4 niveles ya es un poquito mejor, pero aún así los falsos positivos son bastantes y no puede simplemente extraer el circuito como lo hacía antes. Muchas de las seguridades todavía dependen de oscuridad, ¿no? Si ustedes quieren abrir un circuito, esta es una buena forma de hacerlo y ya demostré que varias veces de que entre más layouts se puedan generar, pues más mejor se puede hacer y entre más complicados sean los circuitos, más falsos positivos. Entonces, una de tantas cosas para poder automatizar la seguridad de un circuito que usted quiera digamos hacer. Este es otro que hicimos recientemente en el laboratorio. Es un generador de ADCs. Entonces, principio bastante sencillo, es ese circuito que se encuentra en la esquina, utilizando varios CDACs, pero entonces, si ustedes solamente tienen las celdas estándar, esto es bastante útil, porque si ustedes ya tienen las celdas, significa que simplemente es reutilizar esas celdas simplemente conectadas de una forma específica para poder hacer capacitores o los comparadores o bueno, los switches, lo que sea. Están reinvitadísimos a leer este paper, está completamente abierto, está en Display Explore. Aunque yo no hice el diseño, yo sí hice la automatización. Entonces, simplemente yo aprovecho que todo ya se encuentra en estándar Cell. Entonces, yo simplemente comienzo a ubicar utilizando scripts. Creo que no lo coloqué aquí, pero cada una de las posiciones de las estándar Cell se encuentra ya en un tipo de matriz. Y los CDAC se van expandiendo de adentro para afuera. Entonces el 0 va más abajo, luego el 1, luego el 2, luego el 3 y se replica para la parte de arriba. Entonces yo implemento esto y entonces no es más sino una nueva tecnología que ya no está utilizando 180 sino quiere 65. ¿Aló? Bien. Sí, pueden diseñar un nuevo AS en cuestión de horas. Y eso no se escucha en ningún lado. Lo malo de este tipo de arquitecturas que utilizan solamente transistores para hacer los CDACs es que debido a la linealidad de los transistores en sí mismo no puede tener buena conversión. Esto simplemente puede llegar, en este caso solamente es hasta 8 bits, en el caso de 65 nanómetros. Pero entre más sofisticado sea la arquitectura, pues esto se puede de pronto empujar un poquito más. Y pues simplemente sería generar ADCs en cualquier momento que se quieran. Y este es uno más reciente. Este lo hice hace 3 semanas. Eso fue parte de lo que estábamos haciendo. Necesitábamos un PLL y necesitábamos que ese PLL fuera hasta más o menos 500 MHz. Yo me pasé un poquito aquí y lo hice hasta 1 GHz, pero pues me perdonarán por eso, pero simplemente le coloqué un divisor al final y pues ya se arregla, ¿no? pero bueno, cuando comencé a leer los papers, esta fue la tabla que me interesó. ¿Sí ven? Ustedes se dan cuenta de que entonces, si lo hacen análogo, pues sí, más o menos en medio año, con buena suerte. Porque es que requiere mucho posicionamiento, mucho cuidado con el layout, mucho de todo. Es bastante difícil diseñar un PLL. Los sintetizadores de frecuencia tienen mucho problema al momento de manejar su precisión. Entonces, para hacerlo bien preciso, siempre se requiere mucho cuidado al momento de diseñar y al momento que usted diseñe, tenga su circuito ya completamente verificado que va a funcionar bien esto con sus variaciones y todo eso. Ahí es cuando usted se pone a hacer el layout. Y con el layout también sigue siendo difícil porque, por ejemplo, el oscilador, el RF, necesita mucho cuidado y no puede haber layers de nada interfiriendo en el inductor. Por eso es que toma mucho tiempo. ¿Yo qué hago acá? Pues comenzaron a decir de que, mire, el phase noise, pues aunque no es idealmente lo mejor que se puede hacer, de todas maneras, dependiendo de qué tipo de arquitectura use, el mejor que he encontrado fue este ILPL, que significa que inyecta parte del edge, del reloj, de referencia, como parte de la salida. Entonces cada referencia está inyectando, está forzando la inyección de la salida del PLL. Por eso es que lo llaman injection loop, injection lock PLL. Y con eso pueden subir bastante la eficiencia. Y lo bueno de esto es que es completamente digital, porque es que lo único que usted necesita para esto es un oscilador de anillo. Y al momento de usted implementarlo con este tipo de inyección, el ruido de fase, pues esto se decrementa, porque usted está forzando literalmente a que la fase se esté sincronizando cada referencia. Entonces, prácticamente usted está ignorando los problemas de fase del DCO. Entonces, muy bueno. Y sí, me demoré una semana. O sea, pues, si usted simplemente ahí medio lee el paper y pues esto lo implementa, pues esto ahí tiene un PLL. Y bueno, a partir de ahí ya será mejorarlo, mirar a ver si funciona mejor esto después. La cosa es que al menos se mueva. Ya lo mandé a fabricar, entonces pues miremos a ver cómo sale. Bueno, esto es un poquito más de detalle cómo funciona, ¿no? Yo no soy diseñador de PLL, ¿no? Pero entiendo la importancia de lo que es el phase noise. Porque si usted no es lo suficientemente preciso, lo que puede estar pasando son variaciones en la fase, y eso afecta al fin y al cabo el performance del circuito a donde lo quiera conectar. Entonces, no tiene sentido que yo haga un PLL sin analizar precisamente el phase noise. Entonces, ustedes se dan cuenta de que pues la gris es prácticamente el DCO, el ring oscillator, el de siempre. Y a partir de ahí la azul es la que ya tiene su forma final y las diferentes aportaciones de ruido al fin y al cabo. Al fin y al cabo se concluye que el que más aporta ruido siempre va a ser la inyección en sí misma. Entre mejor esté diseñado eso, pues mejor. De resto, no es más sino tratar de hacer lo más lineal posible los delays del ring oscillator. No puse gráfica aquí de cómo se coloca. No, creo que no lo hice. Pero básicamente usted le cuelga una NAND, y si usted le cuelga una NAND y lo prende y lo apaga, la capacitancia cambia. Entonces simplemente está haciendo que el delay cambie de una forma fina. La coarse, las de allá son las finas, perdón. La coarse, esto sí es más de ponerle más inversores. Bueno, en este caso son NANDs. Y lo afecta en el rango ya va de 100 a 500 picosegundos, y ya por eso ya afecta un poquito menos. Entonces el rango se va haciendo más fino. Y a partir de ahí es ponerle los filtros. Se puede utilizar filtros digitales para esto, y lo coloca directamente a la salida y ya tiene su PLL. Entonces así es como funciona. Bastante pequeño, bastante rápido de implementar. Simplemente coloca ahí, y ya no es sino cuestión de hacerle press and route. Obtengo la extracción, verifico que funciona, o sea, le hago este mismo phase noise pero por fuera, ya después de extraído, y después escoge a ver si se utilizan mejores celdas para eso. Entonces de pronto los rangos de estos delays ya no son tan buenos, entonces tocaría utilizar otros. Pero esa es básicamente la cosa. ¿Por qué estoy diciendo esto? Les acabo de introducir tres circuitos diferentes analógicos que puedo hacer completamente automáticos, ¿sí? Mi visión siempre ha sido la que puso el grupo on chip desde ya 2015. Prácticamente poder generar nuestros propios microcontroladores ¿Y por qué microcontroladores en específico? Porque pues tienen todo integrado en un solo circuito. En realidad el término verdadero se llama SoC, System on Chip. Y para eso ustedes necesitan circuitos analógicos. Lo que pasa es que, como ustedes se dan cuenta, por más de que nosotros tengamos diseñadores y tengamos diseñadores muy buenos, el problema es que el tiempo siempre está en contra. ¿Por qué? Porque pues los deadlines, o sea, ustedes tienen un deadline que cumplir para poder someter el circuito a fabricación, y por lo general no alcanzan. Simplemente los tiempos de diseño son bastante grandes. Entonces, si quieren hacer un prototipo de cualquier cosa, así es como yo envisiono que se haga. Entonces, no solamente el circuito digital, que es lo que tenemos arriba. Esto es un circuito bastante viejo ya, llamado Guerini, ya lo han escuchado de pronto. El caso es que no solamente lo digital, que pues generadores ya existen. No consideré colocar los generadores digitales acá porque pues ya son bastante evidentes, pero tiene un generador de circuitos digitales. Y ya teniendo generadores de circuitos analógicos, colocar un chip entero solamente ya es cuestión de semanas. Y esa es la idea. ¿Y qué tiene que ver esto con AI? Lo que pasa es que si ustedes le preguntan a ChatGPT cómo se hace eso, ya sabe que esto no le va a dar el circuito. Pero lo que sí pueden hacer es, en cada uno de estos procesos que acabo de mencionar, meterle AI. Entonces, quiero que me haga un PLL de este tipo de circuito. Como ya tiene usted un generador, no es más sino coger la salida del ChatGPT y ponerlo ahí. Y entonces ya tiene su circuito que literalmente cogen desde AI y les genera parte de su circuito. Y después viene el siguiente y el siguiente. Mi punto aquí es que la automatización es más importante que usted mismo haga la automatización, y cuando ya ustedes entiendan la automatización, cuando lo vayan a pasar a AI, es cuando ustedes ya comienzan a visualizar esto que se puede automatizar todo. ¿Y quién haga esto? Son millones de dólares. Yo no he podido, pero pues ahí está, ahí está planteado. ¿Cuáles son? Y 46. Hagamos preguntas. Hagamos una ronda de preguntas. No. ¿Seguimos? Listo. Vamos a entonces el otro pedazo Sí, mejor hagamos preguntas, ¿no? Porque es que si no ya paso al otro lado y pues queda esto en el aire. Entonces, hagamos una ronda de preguntas y seguimos.
Bueno, sé que tiene preguntas.
Gracias, Cristian. Una preguntita que no termino de consolidar la idea completamente de automatizar completamente el layout analógico, en el sentido de, creo que tú mencionabas es hacer el mismo equivalente de celdas estándar que utilizan las librerías digitales, hacer un equivalente de celda estándar analógica. Pero a partir de allí, digamos que los diseños podrían no ser implementables con una única celda, sino con una variación. Es que la palabra es analógica, o sea, digamos que no concibo la idea de implementar un circuito analógico a base de la misma celda que puede tener una única dimensión o algo así. Si me voy a entender, ¿podrías un poco elaborar esa idea?
No para nada. Mira, es paradigmas, al fin y al cabo. Si nosotros nos metemos en la historia de qué tipo de circuito es el que usted tiene que hacer para lograr su diseño, pues cualquier cosa vale. O sea, Vamos a la historia de la ADC, por ejemplo. El problema de esta ADC es que no es tan performante porque la linealidad de los transistores, cuando se utilizan como capacitores, no es tan lineal. Eso jode bastante, perdón la expresión, jode bastante la eficiencia, y en el momento de que vaya a los LSB, que son los más pequeños, simplemente no es capaz. Es decir, la linealidad ya se jode y no es capaz de ir más allá de 9 o 10 con una buena tecnología. Lo que siempre digo es que hay un trade-off. Mi punto aquí más es en el sentido de que usted quiere algo rápido para poder probar su teoría. Es mejor hacerlo modular, lo que yo digo, lo que yo quiero decir. Entonces, en el caso de que utilice solamente transistores, este es muy bueno. Pero ya si usted quiere utilizar los propios los capacitores, que sí son los mount caps, por ejemplo, pues ya no es tan evidente, y sobre todo usted tiene que mantener un tipo de simetría para mantener, digamos, su linearidad intacta. Entonces, la idea es más bien coger entonces ese CDAC, perdón, cada uno de esos capacitores, ponerlos en alguna forma estándar, con tal de que usted sepa que cuando usted lo conecta horizontalmente o verticalmente, de una vez ya lo tiene conectado. Es como la filosofía que quiero colocar acá. Cuando nosotros hablamos de celdas estándar, la celda estándar que nosotros conocemos, la digital, se conecta horizontalmente por BD y BCS. Eso es todo lo que hace. De resto, simplemente coge de aquí a allá para hacer el ruteo. Y las herramientas están muy evolucionadas para resolver ese tipo de problemas. En analógico puede ser similar, y el problema que siempre veo al momento de hacer diseño analógico es que al momento de hacer el layout tiene que tener demasiado cuidado con el layout. Si no el performance se le va. Entonces, pero todo comienza siempre desde el diseño. Usted siempre tiene que tener el diseño a la mano. O sea, usted comienza con el transistor, como comienza con las simulaciones, pero lo que yo quiero dar a entender es que si hay una forma de mantener esa conexión entre cómo va a ser el layout al momento de diseñar, el tiempo se reduce. Entonces, yo no diseñé este circuito, ahí está, ese circuito que se encuentra allá, y ese tiene su diseño. La cosa es que esta persona lo que hizo fue pensarlo en standard cells. Entonces, él experimentó con 2 o 3 tipos de switches, y se dio cuenta de que el mejor switch que podía utilizar era uno que se podía balancear por 2 lados por los transistores P y N de los inversores. Entonces, literalmente hay transistores que están perdidos al momento de utilizar el inversor, pero mantiene muy bien la linealidad, incluso mejor que el pass gate. Entonces, viene el diseño al fin y al cabo. O sea, la idea es pensarlo que al momento de que usted quiera ya hacer el siguiente paso, que es el layout, que le sabe que va a consumir el tiempo, aquí es donde usted lo puede optimizar. Sería el punto de ahí. ¿Otra pregunta está bien?
Sí, yo tengo una pregunta, digamos, referente al diseño analógico. Uno de los, digamos, de los retos del diseño analógico es hacer como toda la verificación para estar seguros de que cuando se mande a fabricar ese circuito funcione, porque, bueno, puede ser muy costoso, y donde no llega a funcionar se tira todo el proyecto. Digamos, en este contexto, ya que hay muchos problemas, por ejemplo, lo que usted mencionaba sobre la linealidad, ¿qué tan efectivo en realidad, aunque sea un tema nuevo, llegar a que, por ejemplo, si este ADC no es el enfoque del System on Chip, que esos errores no afecten, digamos, lo que se quiere medir, si es solamente como un bloque de paso que se necesitaba, pero no se quiere invertir tanto? O sea, ¿hasta qué punto sí es viable ahondar en ese tipo de temas, ya que pues, el diseño analógico podría tirarse todo el proyecto si no llega a funcionar.
Volvamos a esta gráfica entonces. Mi problema siempre va a estar con las herramientas. Mira, la verificación que ustedes hacen, que todos hacemos en analógico, yo también la hago, consiste al fin y al cabo en hacer análisis matemático de lo que sea que usted quiera hacer. En el caso de una ADC es la linealidad y el ruido. Entonces, Virtuoso es muy bueno para poder hacer ese tipo de análisis. Está todo completamente acomodado. Está ahí simplemente para que usted coloque la salida digital de su ADC comparado con la salida ideal que debería ser. Los coloca, le hace FFT, le hace cualquier tipo de cosa o hace simplemente análisis de puertos. Y yo le voy a poner una cosa. ¿Usted sabe cómo hacer esto? Análisis de puertos en un circuito, cualquiera. Probablemente en teoría ustedes lo saben, pero en el momento en que ustedes utilizan las herramientas de repente se olvida. Este es el paradigma que les estoy ofreciendo. Ustedes están utilizando la calculadora y como calculadora como tal le deja toda la vida fácil. Usted simplemente tiene que sumar, restar en una calculadora ahí y se olvida de que tiene que hacer cálculos. Entonces, las herramientas son muy buenas si la sabe usar. La cosa es que no puede alejarse de los principios que se aprendieron pues, al momento de analizar circuitos. Cuando yo hice la verificación de la ADC, pues mi compañero no sabía cómo sacar los cálculos que él hizo. Había un par, no me acuerdo cómo es que se llama, uno era el FFT y el otro es para analizar el ruido, la linealidad del ruido, no me acuerdo cómo se llama. Pero lo que yo hice, literalmente, como yo tengo un generador en Verilog, lo puedo pasar muy fácilmente a Spice. Lo simulo en Spice y tengo un CSV. Y ese CSV lo meto a Python, ya. Y a partir de ahí es calcular cada una de las cosas que ya le ofrece directamente Virtuoso. Entonces, si lo quiere hacer en esto, Virtuoso está muy optimizado y es muy buena herramienta para poder hacer su diseño de circuito, su prototipo. Pero a la misma vez lo enlarga demasiado porque prácticamente usted está dejando que la herramienta le haga todo. Entonces, y se supone que deja eso ahí a que funcione y si la herramienta le dice que luz verde está bien y si no, pues no. Entonces, ahí está. La cosa es tener las dos buenas. Entonces, por eso es que vuelvo a este gráfico. Si tuviéramos herramientas libres, en un mundo ideal, donde todo esto estuviera funcionando bien, no es más sino modificar el código libre y poner ese tipo de tight integration, esa integración completamente anidada, completamente disponible en el campo abierto. Y con eso usted puede hacer sus verificaciones muy bien. Lamentablemente no vivimos en un mundo ideal, entonces eso no existe. Y por arriba no se puede, porque pues todas las herramientas están muy específicas para hacer solamente ese cálculo y ya. Entonces no lo puede exportar más. Yo entiendo su preocupación de que cómo usted hace para verificar todo esto. Mi respuesta es más bien deje de estar utilizando Virtuoso.
¿Alguien tiene alguna otra pregunta?
Ok, bueno, mi pregunta va, pues, digamos que pensando en hasta cuál es el alcance de los circuitos que puedan ser sintetizables, los analógicos, pues. Digamos que el SAR, el ADC que usted usó, pues en cierta manera es muy fácil, es relativamente amigable a la sintetización porque pues tiene muchos bloques muy digitales, a pesar de que el funcionamiento sea analógico, porque pues lo digo pensando en quizá hay bloques más analógicos donde ya no hay ya el transistor ya no es solo un switch, también está la parte de la amplificación, entonces sí, estamos más cerca de la parte física, Entonces, ¿cómo podríamos, hasta qué punto podríamos acercarnos a esta parte física desde ese approach de la sintetización de esos circuitos?
Mi generador no es el único que existe, hay otro más. Está el BAC 3, se supone que ya está disponible. Yo no lo he visto funcionando, pero ahí está. Pero para eso existen ese tipo de herramientas. La cosa es que usted meta su circuito en un tipo de generador de estos. Lo que pasa es que, bueno, el problema principal que yo le estoy viendo es que cada circuito que usted haga analógico tiene algo demasiado único o demasiado difícil de implementar. Digamos, si usted está utilizando una combinación entre MOMCAPs y transistores de alto voltaje, cada una de esas tres tecnologías utiliza algo diferente. Y es por eso que casi no se puede implementar automático, porque entonces usted tiene que hacer una parte específica para su MONCAP, otra para el transistor de alta y otro para la interfaz, para el buffer. Entonces, yo digo que la solución es más tratar cada uno como bloques separados. Entonces, el límite es prácticamente lo que usted se permita hacer al momento de hacer sus bloques. Nosotros sabemos que tienen que estar tight couplers, sí, tiene que estar sí o sí juntos. El momento de hacerlo automático, pues usted tiene que saber que tiene que estar juntos. Eso es todo lo que tiene que hacer. Pues nada, simplemente hacer su layout de cada una de esas cosas con tal de que quede completamente tight couple. Y luego es copiar y pegar, porque mucho de lo que se está viendo es copiar y pegar. Lo que siempre veo que se pierde mucho tiempo es que usted utiliza la herramienta de virtuoso, que es simplemente hacer la matriz, y muy buena para hacer las matrices y todo eso, pero en el momento que usted lo quiera hacer ya no son 12, son 14, 16, 18, le toca estar a cada rato haciendo otro layout más, otra cosa más. Y los cambios lo que más jode a un diseñador analógico son los cambios de diseño, porque es que se le olvidó este tipo de diseño, este design constraint que pasó por ahí. Nada que hacer, le toca volverlo a hacer. Si usted lo hace simplemente utilizando comandos, ya, simplemente es cambiar el número, se acabó. Ese es más o menos el punto.
Bueno, entonces ya queda cerrado el espacio de las preguntas y vamos a terminar entonces, esta charla queda terminando 20 minutos antes de las 12.
Vamos a hacerlo rápido entonces. Creando mejores circuitos para aceleración. Esta fue una charla muy interesante que vi en SSCS. Les invito a que de pronto, si se pueden encontrar los slides, de pronto lo vean. Le dice prácticamente cuáles son los niveles que espera la industria al momento de implementar la inteligencia artificial. Ustedes ya ven algunos nombres ahí, el CPU, el GPU y el NPU. En un mundo ideal sería que usted tuviera su propia arquitectura para su inteligencia artificial. El problema es que solamente utiliza esa inteligencia artificial y ya. La derecha es la mejor posible, pero pues estamos hablando de un mundo ideal. La mayoría de lo que está usando es NPUs. Que es más o menos el pedazo que está haciendo en este momento las grandes empresas. Mire, parte de las cosas que se hacen en la industria al momento de hacer aceleración de AI es lo que nosotros llamamos primero la reducción de cuantización. Entonces, yo sé que esto puede verse un poquito complicado, no lo es en realidad. O sea, al fin y al cabo lo que están haciendo es lo que se encuentra aquí arriba. O sea, ustedes van reduciendo a cada rato los cálculos de una mantisa más grande a una mantisa más pequeña. Y ya estando en el núcleo es cuando se hace la mayoría de los cálculos, y luego se vuelve a hacer más grande, en ese momento es cuando ustedes sacan la salida de su circuito. Entonces ya depende de qué tipo de mezcla hacen. En este caso lo que hacen es hacer un mixed precision. Entonces, literalmente pueden combinar dos tipos de precisiones muy bajitas para poder hacer estos circuitos. Y la ventaja de AI en este caso es que todos los cálculos pueden ser imprecisos. Al momento de hacer una suma no tiene que dar la suma exacta, simplemente puede dar parte de la suma, puede dar simplemente los más significativos, o si en el caso de multiplicación puede ser algo que sea cerca a la multiplicación. Entonces no sé si estaba por aquí. Sí, creo que este multiplicador es parte del diseño y el otro es el que se encuentra con el scoring allá. Entonces, estos son dos formas de hacer suma y multiplicación, que reduce definitivamente el área, y con eso usted puede hacer más cálculos en la misma área. Esos son prácticamente los trucos que todo el mundo está haciendo. O sea, si ustedes miran cada uno de los papers más importantes, eso es lo que ustedes van a ver como un patrón. La otra es Computing in Memory. Este Computing in Memory es tal como suena. Ustedes utilizan una memoria y esa memoria internamente hace el cálculo de multiplicación y suma a la vez. Puede ser analógica y puede ser digital. Yo puse aquí una analógica y una digital. La digital es esta de acá, la analógica es la de allá. Entonces, si estamos hablando de analógico, es muy sencillo de implementar, porque eso simplemente es el transistor pegado al resto de transistores que se encuentran en la columna, y eso hace una suma directamente. Depende de qué tan grande es el transistor que le está pegando ahí. Ese es el peso que le coloca. Entonces, por lo general es fijo. Y entonces hace la suma. Al final de esta línea se encuentra la de C, y esa es la salida del coso. Ok, perdón, la de la derecha. Estamos hablando de la derecha, perdón. Entonces sí, son transistores sencillos dependiendo de qué tan grande sea el transistor. En la parte de la derecha, esto introduce el peso, entonces cada transistor tiene su peso, suma todo eso y al final se encuentra una DC con otra resistencia. Al fin y al cabo se convierte en un amplificador, un op-amp negativo ahí, le coloca la DC y tiene su multiplicación y su suma. Y no es preciso, no necesita hacerlo. Entonces simplemente usted coloca con un DAC por el input driver lo que usted quiera, o simplemente coloca sus unos y ceros directamente en las líneas, y eso también es válido. Depende de qué sabor es el que quiere, y eso es lo que se puede hacer. Ya cuando es digital, se aprovecha de que o sea, las RAM están implementadas en cierta forma de que cuando obtiene el bit directamente ya va al sumador o al multiplicador. Entonces con eso ahorra área. Y otra cosa que se ahorra área es lo que vimos antes, que es la reducción de cuantización. Entonces se hace la multiplicación y la suma directamente ahí, y en este caso, por ejemplo, utilizan shift y adder. Entonces el shift hace la multiplicación, la suma hace la suma. Entonces, sencillo de entender en la izquierda. Esta es ya un poquito más complicada. Yo pienso que la voy simplemente a omitir, pero es simplemente una versión más complicada de lo que acabamos de ver. Que para abrírselo un poco de abrebocas, aquí lo que aprovechan es que todo el MAC se hace en paralelo. El MAC significa multiplicación y adición, ¿no? Entonces, por cada circuito de reloj que se hace ahí, la multiplicación se hace a la misma vez que la suma, y cambia los modos dinámicamente por cada una de las celdas. Entonces pueden tener precisiones variantes al mismo tiempo adentro. Entonces no necesitan tener una capa, solamente hacer una capa de cálculo para los más imprecisos, sino puede hacerlos menos imprecisos dinámicamente. Con eso ahorran en latencia. Entonces simplemente lo hace más rápido, más sofisticado, pero es el mismo principio. Listo. Y ya nos vamos un poquito más a tecnología. Algo que está haciendo mucho la industria es esto de los interposers. Usted se va a dar cuenta que todo lo que se encuentra en este momento en la industria es conectar las líneas de datos lo más cercano posible entre circuitos. Porque el problema más importante al momento de hacer aplicaciones de inteligencia artificial es el movimiento de datos. Entonces, un circuito puede estar haciendo el AI, el otro puede estar haciendo simplemente otro tipo de cálculos. El caso es que al momento de sacar el resultado de AI de un lado y moverlo al otro, pues si lo conecta únicamente utilizando la PCB, la latencia es demasiado alta y no va a alcanzar. Por más de que usted utilice interfaces analógicas así bastante a gigahertz, no va a alcanzar y simplemente no va a pasar de cierta frecuencia. Entonces, ahí lo están viendo, o sea, bastante chips metidos entre sí, sanduchados, y con un interposer que también es hecho en silicio. Entonces, con eso es que hacen las conexiones entre chips. Esto es prácticamente lo que está haciendo Apple. Apple, cada uno de los empaquetados que ustedes tienen ahí, tiene como 2, 3 chips por empaquetado. Yo creo que más. Pero así es como lo están haciendo en este momento. Esta referencia es de Samsung, by the way. Y aquí tiene una versión más profesional. O sea, cuando ustedes ven esto en la industria, así es como se lo muestran. Pero al fin y al cabo ustedes se dan cuenta de lo mismo que acabamos de ver. O sea, la única diferencia es que como ahora ellos tienen acceso a las tecnologías de DRAM, ellos colocan el cálculo de la computing memory dentro de la DRAM. Entonces, o en la interfaz de la DRAM. O sea, pero no dicen mucha información de eso. Eso simplemente qué es lo que están haciendo y simplemente muestran los valores. Pero cuando ustedes se encuentran ahí adentro no es muy diferente a lo que ya se encuentra digamos en la academia. El mismo principio, solamente que expandido a la plata que tienen, ¿no? A la tecnología que ya tienen. Y ya para terminar, entonces voy a introducirles brevemente el neuromorphic que yo hice, que nosotros hicimos, perdón, para acelerar la inteligencia artificial. Como ya les había dicho antes, nosotros imitamos la neurona, perdón, y un modelo que es bastante preciso es el de Leak, Integrate and Fire. Es el acrónimo que ustedes ven ahí en la derecha, que se llama LEAF. Básicamente, al momento de mirar una celda biológica, los iones de sodio van pasando la barrera y se van acumulando en la neurona. El momento en que llega a un límite es cuando la sinapsis dispara una diferencia de potencial. Y nada, entonces si ustedes literalmente ustedes pueden imitar esto con un capacitor y un comparador. Entonces esa es la básica, el básico Liquid Integration and Fire. Han habido bastantes aplicaciones. Esta es una de mis favoritas, que coloca muchas de esas neuronas en una elipsis. Puede ser una elipsis, puede ser completamente aleatorio. A eso le llamamos el reservoir, porque literalmente todas las neuronas se encuentran aleatoriamente conectadas. Y como son aleatorias, pues puede conectarlas como quiera. Puede ser un grid, puede ser aleatorio, puede ser un círculo. En este caso un círculo. Como ustedes ven ahí, de izquierda a derecha, el DAC va convirtiendo todas esas pulsos hacia voltajes por cada una de las neuronas, y la suma de todas esas voltajes, cada uno tiene su propio ADC ahí, o bueno, cada uno no tiene su propio ADC, de pronto hay como 10 o 11, pero van mostrando cada una de las neuronas y las suman todas para poder tener su resultado. Lo que se encuentra dentro del reservorio es completamente aleatorio, incluso los pesos. El aprendizaje se hace acá, en la izquierda arriba, en esa Z igual a sigma BW. Esos son los pesos que cambia dinámicamente para tener su respuesta, de acuerdo al training. Esto es muy rápido de aprender. Esto solamente toma 400 muestras, por ejemplo. Al momento de colocar simplemente las primeras 400 muestras, o a veces menos, 100 muestras a veces es suficiente. Y ya después ya aprende directamente a hacer esto. Esto es bastante rápido y bastante eficiente en cuestión de potencia. Esta es otra, pero pues la voy a colocar. Esto es lo que yo estaba hablando hace poco. Entonces este es un link que se integra en Fire. Si usted lo quiere imitar, no es más sino colocar algún tipo de circuito que coloque potencial adentro del RC. El C va acumulando, pero el R te va descargando a la vez. Entonces eso se podría ver directamente como la suma y la multiplicación. Hay suma para arriba al momento de meter los pulsos y hay suma para abajo en el momento de caer. Entonces está haciendo cálculos. Y la salida no es más sino el fire que se encuentra. Entonces en ese momento es que usted las conecta entre sí. El cómo las conecta entre sí y qué es lo que hace entre ellas para comunicarse es parte del arte de este tipo de arquitecturas. En mi caso lo hicimos de esta manera, pero entonces no tengo detalles sobre esto precisamente. Yo pienso que esto es lo mismo de antes. Pero yo hice una neurona. No voy a dar detalles de la neurona, no puedo darlas, pero pues ya el paper se encuentra por ahí. Pienso que simplemente lo pueden leer y ya. Pero lo que ven a la derecha es la neurona, lo que se encuentra ahí en pequeño, que al fin y al cabo no es el mismo RC, pero el RC solamente lo hago con transistores. ¿Por qué? El leakage del transistor ya tiene su resistencia y el capacitor es el capacitor. Entonces pues un N y un P, y en el medio es donde está el voltaje que yo quiero acumular. Eso es todo. A eso le pegué un VCO, un oscilador controlado por voltaje, y esos son los pulsos que yo saco. Eso es todo. Como toda la entrada es digital y toda la salida es digital, coloqué todo en una FPGA. Entonces las conexiones que se hacen desde una neurona hasta la otra pueden ser completamente aleatorias para cualquier tipo de experimento que se haga. En este ejemplo en especial colocamos 100 neuronas juntas, pero ya hemos hecho prototipos que tienen hasta 1000 neuronas puestas en un espacio de 2 milímetros por 2 milímetros. Entonces es bastante eficiente. Este es el setup de medición. Este cable es porque me equivoqué en el momento de diseñar la PCB. Siempre pasa, no se preocupen, les pasa a los mejores. El caso es pero lo que hace esto es simplemente conectarlo directamente a la FPGA, a una FPGA que se encuentra abajo. Esa es la que me hace los cálculos y me captura las señales para poder simplemente mostrar. Entonces lo que hace la FPGA abajo no hace más sino muestrear y calcular el resultado final. Pero prácticamente todo se hace dentro del reservoir. Aquí ustedes se dan cuenta cómo es que funciona. En el momento de que esta entrada es externa, en el momento de que yo hago de abajo para arriba, eso se traduce en un pulso hacia adentro del chip. Y ustedes se dan cuenta de que yo no puedo ver directamente el voltaje porque no coloqué ninguna DC, pero yo puedo medir la frecuencia de este oscilador. Entonces ustedes se dan cuenta que el oscilador de pronto no se puede ver muy bien, pero aquí es más delgado y allá es más gordito. Entonces con eso demuestro el principio de cálculo que se hace dentro de las neuronas. Uno de los algoritmos que estamos usando es el force algoritmo, que es prácticamente realimentar la salida que se encuentra de toda la neural network y ponerla hacia adentro. Y se utiliza este algoritmo de abajo que se llama RLS, que no es más sino un filtro dinámico. Detalles de ese algoritmo son bastante interesantes. Simplemente es una multiplicación de matrices, muy similar a lo que se hace con ¿cómo se llama? Se me olvidó, pero bueno, el que se utiliza para linealizar puntos con la línea. Regresión lineal, gracias. Regresión lineal, muy similar a esa. En este caso lo que hago es hacerle aprender una sinusoidal. Siempre dependiendo de la frecuencia, porque depende mucho de la frecuencia de muestreo y otro tipo de cosas que se encuentran dentro de las neuronas. No funciona para todas las frecuencias, pero ustedes se dan cuenta que ya se está disminuyendo la precisión en 180 Hz, pero ya en 200 Hz, 220, 250 ya se encuentra bien. Otros resultados más por allá hasta 400 Hz, ya 400 Hz ya no es capaz, pero se nota que este tipo de reservoir puede aprender con retroalimentación. Esto es lo mismo pero con Sawtooth, perdón, este es el Sawtooth y esta es la triangular. Entonces, ya depende de qué es lo que le coloque, pero pues tiene cierto nivel de precisión, dependiendo de qué es lo que le coloque. Entonces, sí se demuestra que puede aprender. Así es como evoluciona más o menos. Ustedes se dan cuenta que estos son los pesos que pasan por el tiempo. Y hasta aquí es donde se hace a la mitad, hasta donde se hace el aprendizaje. A partir de ahí los pesos de afuera se dejan quietos y se deja que el circuito simplemente corra por sí mismo. Y entonces ustedes se dan cuenta que en el momento de que termina de aprender, ya queda aprendido para ese tipo de sinusoidal que le coloqué. Entonces funciona y es bastante rápido, o sea, un setting time de 20 milisegundos, difícil para una inteligencia artificial, ¿no? Me hago entender. Es bastante interesante. Otra es esto, ya es open loop. En este caso lo único que hago es colocar una excitación en la entrada, medir lo que sea que salga todo y luego calcularlo al final. Entonces esto no es retroalimentativo. Esto es con una señal digital. No se alcanza a ver mucho aquí en los chicos, pero pues esto es una señal digital que va de 1 a 0 y esta es la respuesta de la red neuronal. La intenta seguir y esto es aprendizaje de una SOR. Entonces está haciendo que la muestra n-2 y n-1 SOR sea la salida. Eso es lo que quiero que aprenda. Y sí, esto puedo tener correlaciones hasta 23%, lo cual es bueno para ese tipo de circuitos. Otras cosas son la memoria. Entonces, simplemente el aprendizaje es la misma entrada desfasada un número K, de samples. Entonces, por ejemplo, con 4, pues demuestra que es lo sigue bastante bien. Significa que hasta 4, hasta 5, incluso hasta 6, esto tiene cierto tipo de memoria que se puede utilizar en vivo. Y así lo puedo decir, por ejemplo, para otro tipo de memorias. Esto ya es una gráfica de correlación que tanto aprende con respecto a qué tanto delay hay. Ya a partir de 6 o 7 ya no es capaz, pero ya 2, 3, 4 más o menos puede aprender bien. Y esto es memory capacity también, bueno, esto no me importa. Otro más importante es la prueba NARMA. Es una prueba que se hace a este tipo de redes neuronales para mirar qué tan bueno es calculando funciones no lineales. Una de tantas. Es de NARMA 10, NARMA 20, NARMA 8, ya están bien establecidas. Es una ecuación bastante complicada que coge los 10 samples en el pasado y hace un cálculo no lineal. Es multiplicar, sumar, cosas como esas. Y ustedes se dan cuenta que el azul sigue la verde. Entonces, sí es capaz de aprender cosas bastante complicadas. Una vez uno ve esto, uno dice, bueno, ya es capaz de aprender cosas más complicadas. De pronto ya se puede hacer reconocimiento de voz hay hay otras cosas. Estos tiene que ver más con el edge, ¿no? El AI que se encuentra en el edge. O sea, cuando yo hablo de edge, es lo que yo tengo puesto, lo que ya toca a lo último, por algo lo llaman edge. Es reconocimiento de voz, es reconocimiento facial, es text-to-speech, por ejemplo, también. Entonces, si nosotros podemos hacer esto funciona en tiempo real. Si tenemos más neuronas de esto, 1000, 2000, 10.000, ya puede reconocer texto, ya puede reconocer imágenes, ya puede reconocer todo eso en el acto. Por eso es que es tan prometedor. Y es prometedor también incluso para el bolsillo, porque en este caso solamente tenemos 21.7 picojoules por pulso. Eso es bastante bajo. Significa que por cada cálculo que está haciendo, por cada pulso que está haciendo, simplemente 21 picojoules. Mucho menos de lo que está haciendo en este momento con los LLMs y todo eso. Entonces, hay bastante potencial con este tipo de neuromorphic por ese tipo de cosas. Funciona en tiempo real y es muy barato. Entonces, ese es como el punto que yo quería dar. Pienso que esa es toda la presentación. Esto no sé qué pasó, pero eso es prácticamente yo todo lo que quería decir. Espero que les haya gustado y que les haya inspirado un poco esto al hacer circuitos con respecto a inteligencia artificial. No, la inteligencia artificial no les va a tomar su trabajo, y si lo toma su trabajo es porque usted está haciendo mal trabajo. Entonces, simplemente utilicen la AI con la automatización que les mostré, y si quieren acelerar la inteligencia artificial para hacer sus juguetes o las cosas que quieren hacer para, no sé, la excusa que tengan, pues les recomiendo que implementen sus propios circuitos y alimenten la inteligencia artificial. Muchas gracias.
Ahora damos un espacio de aproximadamente 15 minutos para preguntas, ¿o no? ¿Sí hay tiempo para preguntas? ¿Sí? Ok, entonces, no sé si alguien tiene alguna pregunta acerca de la charla.
Gracias, Cristian. ¿Puedes, hablando de la Leak and Integrated Amplifier Neuron, bueno, esa. ¿Puedes elaborar un poco en cómo se codifica la información en los pulsos? Es decir, como mencionabas, es un equivalente biológico de la relación entre las neuronas y los axiomas. Pero entonces, cuando se está implementando la información, las redes neuronales hacen convoluciones de números, y esas convoluciones se codifican a los pulsos, y los pulsos generan ese procesamiento internamente en el circuito, ¿no? ¿Puedes elaborar un poco en esa nube, en lo que yo llamo codificación de esa información a pulsos?
Pues mira, yo no tengo mucho detalle en estas slides. Me gustaría haber traído otro tipo de slides, o de pronto utilizar el mismo truco que utilizó el profesor Ikeda para mostrar otro tipo de slides. El cómo codifica es más, yo pienso que esto es más arte que ciencia, porque el cómo se haga la codificación de eso en específico depende mucho de la neurona que usted está intentando implementar, la arquitectura. Está hablando de la arquitectura. En mi caso, son oscilaciones. Entonces, se supone que yo estoy acumulando hacia un capacitor con resistencia, ¿sí? Y dependiendo del voltaje de ese capacitor con resistencia, estoy controlando un oscilador, un VCO, ¿sí? Pongamos este de acá. Es que no está el oscilador. Pero a esto le estoy pegando un VCO, aquí, estoy colocando un VCO, que va desde 10 kHz hasta 1 MHz, dependiendo del voltaje. Entonces, cuando yo hice el teorema, la teoría una vez extraído todo lo que se encuentra al momento de que funcione, me di cuenta de que depende mucho de la frecuencia, del rango de la frecuencia, y depende también de los pesos que yo le coloque al momento de hacer los pulsos. ¿Qué tanto dura ese pulso? Si es gordo o si es pequeño o si es bajito, perdón, bajito no, delgado. Esto depende de qué tanto vaya a subir o bajar al momento de hacer este tipo de subidas hacia arriba. Puede subir mucho, puede subir poco. Y así es como se habla. Entonces, si usted coloca mucha frecuencia, pues se va para arriba y siempre va a disparar. Dispara, y no hay problema, siempre va a quedar saturada. Entonces, es cuestión de bajarlo, en ese caso la frecuencia. Yo lo que coloqué en este diseño, de acá, cada uno de esos CLVs tiene metido un divisor a la salida. Yo en realidad me di cuenta de que tenía que utilizar divisor 16, tenía que dividir la frecuencia de salida por 16 para que pudieran dar resultados. En otra fue bueno, los pesos. Al fin y al cabo no puedo utilizar todo el rango de pesos, yo utilicé 16, pero en realidad solamente puedo utilizar como 2 o 3. Entonces, eso es otro campo ahí. Y eso es con respecto solamente a esta arquitectura. Hay otras arquitecturas y el cómo se coloca hacia la entrada o hacia la salida depende de cómo usted diseñó esa neurona. Entonces, prácticamente es arte. O sea, depende de qué es lo que usted haya hecho como neurona para poder implementar, interpretar esas señales como salidas o entradas de lo que sea que usted esté implementando como AI.
Tenemos últimos 5 minutos para la última pregunta.
Bueno, ¿puedes ir a los slides ahorita la que estabas mostrando del RC? La red RC que había. Ok, mi pregunta viene, lo que entendí, el BCO muestra lo que hay en esa red RC, ¿es cierto? Entonces, una pregunta, ¿qué es lo que está entrando a la neurona? Y relacionado también a lo que está entrando, supongo dependerá de justamente las entradas que se multiplican por un peso. Entonces, ¿qué son los pesos en este circuito? ¿Cómo se modifican los pesos?
En ese caso, sepa que la salida de la neurona siempre va a ser una oscilación, esta oscilación de arriba, ¿cierto? Entonces, ¿usted sabe cómo crear un generador de pulsos? Muy sencillo, un inversor con una AND. Ahí está, eso es, no es más. O sea, yo le pego eso y los inversores pueden ser configurables. Yo lo que coloqué fue de 1 a 16. Me di cuenta que solamente, y no coloqué inversores, coloqué delays, el más pequeño que puedo encontrar. Entonces me di cuenta que los delays eran demasiado pesados, entonces solamente pudo funcionar de 1 a 3. Entonces, cada uno de esas oscilaciones cuando va de abajo para arriba, entonces cuando es rising, eso es lo que se le coloca a un transistor P o a un transistor N, cualquiera de los dos. Entonces, el leaf que yo hice es balanceado, significa que yo tengo un transistor P y un transistor N, y entonces idealmente el settling voltage es 0.5 si el voltaje de alimentación es 1. Entonces yo puedo decrecer y yo puedo crecer. Uno de esos se llama excitación y otro se llama inhibición. Y eso es literalmente positivo y negativo si quiero hacer pesos positivos y negativos. En realidad son 3 delays que puedo manejar, pero con positivo y negativo en realidad son 6. Entonces ahí está, así es como se comunican.
Es más como un cuestionamiento. Alrededor de Spiking hay mucha gente que es muy escéptica dado que introduce ciertas dinámicas temporales que pueden ser difíciles de replicar en el hardware o que pueden influir también en la ejecución. Desde el tema de codificar la información como spikes o hasta incluso el propio entrenamiento de esta red, dado que por ejemplo no podría ser hecho de la manera tradicional que conocemos para la inteligencia artificial, que es con gradientes. ¿Cuál es su opinión y perspectiva hacia el futuro de esta área, teniendo en cuenta todo que hay muchos problemas aún detrás de esto?
¿Usted sabe el concepto de lo que es esto, lanzar toda la pared hasta que algo pegue? Es muy similar, de hecho, pienso yo. Porque si nosotros estamos hablando de inteligencia artificial, los avances que ha habido de inteligencia artificial han sido suerte. Usted le sorprendería la cantidad de modelos fallidos que existen de inteligencia artificial, porque todos vienen de física pura. Los papers que hacen los avances de inteligencia artificial, en principio, vienen de física o de matemáticas. Entonces esto depende de cómo es que se interprete eso, y eso es lo que están así es como ellos ganan plata, los físicos y los matemáticos. Lo que están literalmente haciendo todo el mundo, y yo también, es lanzar toda la pared y mirar qué es lo que pegue, porque entonces si a alguien le pega algo, entonces es cuando viene el siguiente LLM, cuando viene el siguiente DeepSeek, no sé, cualquier cosa que vea. DeepSeek también tuvo mucha suerte. Se dio cuenta de que en realidad usted podía coger partes del LLM y no calcular todo el LLM para poder hacerlo más eficiente. Y es por eso que los chinos tuvieron cierta ventaja durante cierto tiempo, pero los Estados Unidos se dieron cuenta y pues ya lo implementaron como ellos lo hacen, y ya DeepSeek ya no importa. Y todo el mundo está haciendo lo mismo. Entonces, alguien le pega, viene el resto y lo imita, y luego queda ahí en estandarte, nada más. Mi opinión al respecto es que si usted quiere hacer el siguiente AI, pues le toca meterse al cuaderno y mirar qué es lo que calcula. Este fue uno, nada más. Existen muchísimos y depende del tipo de reacción física que se encuentre. Hay algunos con cristales, hay otros con neuronas físicas directamente, y cada uno tiene sus resultados. La mayoría está coincidiendo en que esta de imitar la neurona es lo mejor. Es prácticamente lo que nosotros hacemos en cualquier campo de ciencia. Esa sería mi respuesta.
Bueno, ya cerramos la ronda de preguntas y pues nuevamente agradecer, tal como se le agradeció al profesor Ikeda, al profesor Cristian, pues por la charla que nos brindó el día de hoy. Entonces por favor les regalamos un aplauso. Y ahora la idea es tomarnos una foto todos los que están ahorita en el auditorio por acá, y pues ya son libres luego de eso. Entonces no sé si se pueden organizar por acá. Sí, la trae. Sí. Por favor, apagar el video bien.
Peter, one more quick question. It's about your last name. Sorry about that. It is Harpy or Harp?
Yeah, the second one.
Okay, Harp. Sure.
Yeah, perfect.
Thank you.
Thanks.
So we're going to officially start this talk. So, Sergio? Okay, welcome everyone. Thank you for your attendance here today in this talk, and thank you for also the people that is joining online. Today we have we have a special invitation for Peter Harp, and let me introduce Mr. Harp. He is an associate professor in the Eindhoven University of Technology. He received the master and PhD degrees from the Eindhoven University of Technology, the Netherlands, in 2004 and 2010, respectively. In 2008, he started as researcher at Holst Center IMEC in the Netherlands, where he worked on ultra-low power wireless transceivers with a focus on ADC research and design. In April of 2011, he joined Eindhoven University Technology, where he's currently an associate professor and lead of the Resource Efficient Electronics Lab. His main activities are on low power analog and limited signal circuits. For instance, for biomedical applications, Internet of Things, and Edge AI. Dr. Harp is a TPC member of ISSCC and ASSCC, Associate Editor for TCAS1, Solid State Circuit Society, member at large, and Solid State Circuit Society Distinguished Lecturer. He previously served as TPC member of ISSCC, TPC member and track chair for ESS-CIRC, ESS-ERC, and co-organizer for AACD. Was an IEEE Solid State Circuit Society Distinguished Lecturer in 2016 and 17. And he's recipient of the ISSCC 2015 Distinguished Technical Paper Award. This talk, as you can see, is titled ADC Enhanced Techniques for In-Advanced CMOS Technologies. Mr. Peter, so we can start. At the end of the presentation, we will have some questions, and whenever you want.
Great. Thank you very much for the kind introduction and for organizing today's talk. And good afternoon, everyone. I'm sorry I cannot all see you, but I'm very happy to hear there are many attendees. So for this afternoon's talk, I have quite a bit of slides to cover, and we don't have so much time, so I'm afraid I might sometimes go a little bit quick. But I put a lot of references in the slides, and you can ask the organizers later to get a copy of the slides, and then you can also look up in the references. And also, if today's discussion runs out of time, I will be more than happy to have another more informal type of setting to continue any discussion if you like. So before I get started, I just want to mention that this talk is actually part of the Solid State Circuit Society Distinguished Lecturer Program. So this is sponsored by the society. And if you're interested, I think it is very nice to know that the society has a YouTube channel. And if you go there, you can find many similar talks as this one from many different speakers and many different topics that you can just have a look at. And I think it is very nice material if you want to learn something more. And besides the YouTube channel, there's also a so-called resource center. Now that is not for free, but it is for free if you are a Solid State Circuit Society member. And for students, that fee is quite reasonable. And if you are a member, then you can access a lot more material. It's a bit like YouTube, but then a lot more tutorials and lectures can be seen there. So that is kind of for your information. So having said that, I will move back and focus on my presentation. So today I will talk a bit about enhancement or calibration techniques used in ADCs, giving really kind of a very simplified overview, I would say, and give some examples of what people nowadays do in data converters. So you won't see too much details, unfortunately, but I try to give you a bit of a flavor of what is going on. So I'm going to start with a brief motivation. Why are these calibration or enhancement techniques becoming important, more and more important? We're going to look to some general trade-offs, when it is a good idea to do and when maybe not such a good idea. We'll look to some basic principles which are used in many designs, and then we're going to look to some actual examples from literature, kind of just to see what people at the moment are doing in terms of these techniques. And then I'll wrap up with an outlook and conclusion. So first, a bit about the background. Why do we need such calibration or enhancement techniques? And I put here kind of two different reasons. One is because of trade-offs in the circuit design, and one is if you want to overcome limitations. So if you think about design trade-offs, whenever you make an ADC or another analog circuit, you always have to trade off between different specifications that you want to achieve. And if you want to improve one thing, then usually something else will get worse. Now, if you have a very simple calibration method, for example, to solve the offset of a converter or of an amplifier, if you relax that requirement because you're going to calibrate it, you don't only benefit in that offset parameter, but because you fix this issue, you might be able to make smaller transistors, for example, which maybe makes the area smaller or the speed higher or the power consumption lower. So solving one issue can usually benefit you in different dimensions of the design. So this gives you much better solutions. The second one is about limitations. So whenever you make a circuit, typically if you want better performance, you want better accuracy or more speed, for example, it will cost you more in terms of power consumption or chip area. And that's kind of reasonable. But at some point, it usually becomes really a lot more expensive to get the performance a bit better. This is kind of where you hit a bit of a roadblock or a limitation of the design or the technology. So here also enhancement or calibration techniques can help. They might initially cost you something more, but it might help you to push the boundary further, and then you can really reach a performance region which is otherwise simply not feasible. So for those two reasons, you see that these enhancement techniques are beneficial, better trade-offs or overcoming limitations. If you look to applications, this is also relevant. For example, here you see some data rates for wireless communication like Wi-Fi, or for wireline communication that you use, for example, between servers, or if you have an internet cable. And the standards are continuously requiring higher and higher data rates. So this means also you need better ADCs. They need to be faster. They also need to have higher resolution because we make more complex modulation schemes, and as a result, you need higher resolution data converters. And for other applications, for example, also in wireless communication, you see things like beamforming, where you need arrays of ADCs. And it also means you need to make really good ADCs, otherwise an array of ADCs becomes really too expensive in terms of chip area or power consumption. So also from application, you see that we really need to make steps forward. Now, of course, technology scaling helps us a little bit. We know that we have Moore's law, technology scaling, but this mostly is good for digital design. We can cram more transistors on the same area, and we can get a better efficiency. For analog circuits, though, we don't always get much improvement with technology scaling. For example, the matching is still a limit, or the signal to noise ratio. If you have a resistor, it makes 4 kTR noise, and it doesn't matter if you have a very old or a very new technology, it's still 4 kTR. So there are limitations that don't really change or don't necessarily improve the technology scaling. And also a lot of design rules are becoming more complex. If you go from older nodes to more advanced nodes, then you see that the design rules and the layout especially become really complex, and it makes analog circuit design certainly not easier. So this is why it kind of makes sense to push some of your problems towards the digital domain and try to solve it there. It might be a bit easier and it might benefit from technology scaling. Now I have an important but here, and that is because this is a logical trend, but still be a little bit careful that digital design is also not for free. And as I'll show you later, actually, it can still be quite a burden compared to the ADC. So you have to still balance carefully what do you solve in analog way and what do you solve with digital improvement techniques. So to highlight it a little bit, this slide over here shows you for different data converters with different sampling rates over the years, how their efficiency has changed. So here you see the so-called Schreier figure of merit, which is a metric, a number, a score about how efficient the ADC is. And a higher number in dB means you have a better efficiency. So you see that regardless of the ADC speed, lower frequencies or higher frequencies, the efficiency over time is gradually improving. And these are data points from a few conferences. And there's kind of a black average trend of all the ADCs published. Now, this is a nice improvement trend, but interestingly, if you look to digital efficiency, there is Kumi's law, which is related to Moore's law. And Kumi's law kind of expresses the digital efficiency of a computation function. And if you look to the trend for digital efficiency, that's shown here in gray. And you can see that the digital efficiency is kind of improving at the same rate as the ADC efficiency is improving. It's not going faster, and neither is it going slower. So this means that actually digital is not for free at all. It's kind of scaling similarly as the ADCs are scaling over time. And because of that, yeah, it's still important that if you want to do an analog or digital function, you take a right decision about what is more efficient or more suitable. And so in a bit more detail here, you see some other graphs showing the ADC scaling. I show you before the graph in the middle where we see the ADC scaling for different frequencies. On the left and the right, you see it also for different resolutions and for different ADC architectures. But what all the pictures share in common is that for any speed, resolution, or architecture, you see a reasonably similar improvement rate over the years. Some a little bit faster or slower, but they all improve. So this is good news. It means that really no matter what type of converter you have to make, you can roughly expect that over time we can make them better and better. And it shows that we are doing, I think, good research and that we still manage to deal and work with our technologies. So that's a bit about the background, why this is relevant. In this section, I'm going to show a little bit about the choice whether you should implement something in the analog way or in the digital way as function of the resolution, the sampling rate, and the technology. So in this slide, you see a little bit of a sketch. It's really a sketch about how the power consumption, or maybe also the chip area of a analog or a digital function tends to scale if you increase the number of bits, the resolution of the ADC. So for most analog functions, the power goes up exponentially with the number of bits, usually with 4 to the power n. And this is because if you're limited by noise or by mismatch, for every extra bit, which means 6 dB more of performance, you need to make your components 4 times bigger, or you need to spend 4 times the power consumption in order to get the 6 dB improvement. It's kind of a basic physics fundamental. And here you see the y-axis is logarithmic. So an exponential function here and a logarithmic axis shows up as a straight line. But it's a logarithmic axis, so this is actually the green lines are increasing really very, very quickly. On the other hand, if you make a function in the digital domain, it depends a bit on what function you make. But if you make typical functions like accumulation or addition, or you make a multiplier, typically the complexity of such a function, and thus the power consumption, goes linear or maybe quadratic with a number of bits n. So that is a much slower trend. So as a result, you can see that if your resolution is a bit on the higher side, a digital implementation is usually more efficient. But on the other hand, if you go to a lower resolution, then the analog solution might be more attractive. So in this picture, I kind of arbitrarily put a crossover point at 10 bits. It doesn't need to be. This crossover point can be somewhere else. This is just an example. And it depends a bit on the technology or the function you're trying to make, where exactly the analog and digital curves will be crossing. But often I see indeed somewhere between 8 to 12 bit, for example, is kind of the ballpark where many curves kind of cross. So this is kind of the region where you may have to decide to go analog or digital if you're above or below that kind of resolution. So that's about a resolution impact. So it has a clear impact. If you look to speed, you also see differences. So over here, you see a picture for an ADC. So typically, if you want to make the ADC faster and faster to get a higher sampling rate, at low frequencies, the efficiency or the energy consumption per sample of the converter stays constant. But at some point, it becomes more expensive than that. And this is where it starts to become difficult to get extra speed. So you really have to push your circuit by using more current, and then you lose efficiency. Now, if you use time interleaving, for example, where you put parallel ADCs to get a higher total speed, this will cost you some overhead because you might have to calibrate it, or you need some extra clock distribution to get everything synchronized. So initially, this is degrading efficiency. But the benefit is that you can go to a much higher frequency, and at the higher frequencies, it is actually giving you a performance benefit. So from here, you can see that for time interleave converters, the enhancement techniques are really necessary and useful. So for very high speed designs, these techniques are often really necessary. Another example here is about amplifiers. So converters like pipelined ADCs or sigma delta converters, they have amplifiers in their system. And traditionally, we make them with very high gain amplifiers, make a closed loop circuit around it, and then we get a very good precision, robust behavior, stable over process, voltage and temperature spread, but the efficiency is not that great. And more recently, people start to look at more simplified amplifiers, for example, open loop amplifiers. They're more efficient, they go to higher speed, so they are better in all dimensions here. But the downside is that often they need some form of calibration because they don't have so much open loop gain, and that means you might need to have calibration to deal with the inaccuracy of these amplifiers. And also they might spread over voltage and temperature, for example, so you might even need to calibrate them in the background to deal with temperature variations over time. So that adds complexity. But if you can manage that, then you can benefit from the better efficiency and higher speed. So for both these examples, you see that especially for higher speed performance, the enhancement techniques are useful because they can get you better performance. So the last one is about technology scaling. So what's the influence of technology scaling? So if you look to the analog and digital plot again, especially the digital functions benefit from technology scaling. So you can expect the blue lines to gradually go downwards as function of time because of technology scaling. The consumption will go down. And the green analog curves might also improve a little bit, but not so much because they're limited by noise or mismatch. So it doesn't necessarily improve too much with technology. However, because this y-axis is logarithmic, even if you change the technology nodes, the amount of change of the blue curves is actually not so much. It goes kind of slowly, and you need quite a few generations of technology change before this crossover point is really making a meaningful shift. So that's why I don't think this is helping us too much. It is helping, but really very slowly. On the other hand, if you look to applications like this plot I showed you earlier about communication standards, the increase in bandwidth is actually going much faster than what the technology scaling is giving us. And it also shows that kind of technology scaling doesn't keep up with the application demand. And it means the only way to solve it is by doing smarter circuit design or using more improvement or enhancement techniques to overcome the technology and circuit limitations. So that was a bit about the general trade-offs. And in the rest of the presentation, we're going to look to some different architectures. And you're going to find that for example, the delta sigma and the SAR converters, these enhancement techniques mostly focus on dealing with mismatch and noise. And as soon as you go to the higher speed converters, like the pipeline converters or time interleave designs, then also dynamic or timing or frequency dependent issues start to be of concern. So you deal with settling errors or maybe time skew or bandwidth mismatches between the channels in the time interleaved converter. So these are more difficult problems to solve than the static ones, but this enables you to go to higher frequencies. So before we really go to look to the design examples from literature, I would like to show you some basic principles, trying to cover some, let's say, some basic philosophies which are used quite a lot. And later you're going to see several of these back in the design examples. So once again, these basic principles I'm going to show you by far not complete because it's really a large variation of techniques, but I try to pick a few which are kind of pretty commonly used. So before we go there, I first want to kind of tell you or give you a bit of an overview of what are the different type of problems that we might have in a converter that might need some form of calibration or enhancement. And in this slide, I try to mention some of these errors, and they're classified in random or systematic errors. So with random errors, I mean errors which are noise-like, like the quantization or so the thermal noise, or the clock jitter, which is kind of noise in the time domain. Next to that, you have systematic errors. So those are not statistic, but they're kind of reproducible. And there you can have different types of errors. For example, you can have linear or nonlinear errors. And some errors are in the amplitude direction, like gain errors or mismatch. But you might also have time domain errors, for example, because of settling or time skew. Frequency dependent errors where we have issues with the bandwidth, for example. And many of these errors are also time variant, which means that the error value changes over time because of drift or because it's sensitive to the temperature, for example. So what is important with all these errors is that if you have systematic errors, then you can actually, at least theoretically, you can measure them and then you can predict and compensate them. So this is where you can use so-called calibration techniques, which try to detect and compensate for the errors. On the other hand, the random errors, they're really statistical and random, so you cannot really predict them. And you might predict the RMS, the root mean square value, or the standard deviation, the sigma of that error, but you can't predict the exact value because every time it is a different random error. Now, there might be some correlation, but I mean for the random part, the really truly random part, you cannot predict. So this is important because if you look to improvement techniques, I want to kind of distinguish two items. And the first one is what I call an enhancement technique in this presentation. And it's any kind of technique that can reduce the impact of a certain error. And a subset of these enhancement techniques are calibration techniques. So a calibration technique is a technique that tries to improve the performance by really detecting, measuring the error, and then you want to correct or compensate for them. So from this definition, you can see that calibration only works for systematic errors. It doesn't work for random errors because the random errors you cannot measure and then correct. On the other hand, the enhancement techniques, they might also be able to deal with random errors. There are some examples like chopping or dynamic element matching or noise reduction schemes that can deal with noise even though it is a random process. But calibration really only works for systematic errors. So in the coming slides, I want to show you a little bit of examples of calibration techniques. How do they work and what are some, let's say, some most important schemes of how people are implementing this. So the calibration has always two parts to it. The first one is to detect or measure the error that you want to solve. And the second part is to actually do the correction or compensation to fix, or at least partially fix the error. So in terms of the detection, measuring the error, there are two main schemes. One is foreground, the other is background. If you do a foreground detection of the error, it means that you stop the normal ADC operation. You kind of take it out of the application, so to say, and you put it in a special calibration mode, where you have full control of the inputs and outputs. And then you can, for example, put in a test signal, and then you can measure the internal or external outputs of the converter to get some information about the error. So to give you a very simple example, if the error that we want to solve and detect is the offset of an ADC, you can do this very easy in the foreground method by shorting the input, for example. You force it to 0, and then at the output, you just measure how much the code is different from the 0 code, and that should then be equal to the offset. So this is a very simple foreground measurement. So the advantage of foreground detection is that it's pretty direct to measure it. The downside is that if an error is time variant, if it changes over time, then you can't really do this technique unless you regularly stop the normal operation and you go to a calibration phase again. So that's a bit annoying. The other downside is that sometimes you might need a special test signal, maybe not for the offset, but for example, if you want to measure the distortion of a converter, you might need a test signal with several accurately defined points to be able to measure the distortion of the converter. On the pro side, this technique is kind of direct, so you can really force the input, measure the output. So usually you can detect the error relatively quickly in a not too complicated way. You don't need so much processing usually. So it simplifies the detection method. So foreground is one way. The other way is background detection. So with background detection, you try to measure the error while the ADC is also doing normal conversions for the application where you use it. So that's a bit more tricky because then while it is operational, it's doing something useful, you also want to measure the errors without interrupting or interfering with the useful application. So how can you do that? It can be done in many different ways, and I want to show you 3 examples of how this is done, and these are kind of some popular examples. So option 1 is that sometimes there you can have some assumptions about the signal. For example, the offset might be an AC signal only. There is maybe no DC information, or sometimes your signal is bandwidth limited, for example. And based on those assumptions, you can maybe detect some errors which have a signature which doesn't fulfill the input signal specs. So a very simple example is again the offset measurement. So suppose the ADC is used in a certain application where the input signal that the application wants to convert, shown here in blue, is always free of DC. For example, if you have wireless communication, maybe you do a modulation at intermediate frequency, and then you know there's no DC information in the signal. Or maybe it's an ADC for an audio application, and you know there's no audio at DC, it only starts at 20 Hertz. In that case, if you look to the output of the ADC, you will see your signal of the application in blue. But if you measure on average over a long time, you can still extract a DC value of the output. And if you assume that the input signal was DC free, then the offset you measure at the output should still be the offset of the ADC. So this is how you can still measure ADC offset while it is running an application. The downside compared to foreground cal is that you might need to average over quite a long time to kind of eliminate that blue signal and really only have the offset value. So it takes more time to measure. And offset is a pretty simple thing to measure, as you might imagine. Now, a second scheme, which is very popular, is this pseudo-random noise signal injection. So what you do here is as follows. You have this blue signal is any unknown input signal that the ADC converts because of the application that you want to use. But you add a PRN, pseudo-random noise sequence yourself. So it's kind of a random sequence, usually with a 1-bit signal like zeros and ones. You inject this somewhere into the ADC, and then at the output you measure the response of that noise sequence. So on the digital side, usually you have a block which kind of separates the blue and the green signal. The blue signal goes to your application, and the green signal goes to your calibration engine. And by measuring this kind of green response, you can measure certain errors. And for example, if you want to measure a gain error, then simply measuring the amplitude at the output is a measurement of the gain of the ADC, for instance. And likewise, you can measure more difficult items. So the downside of this scheme is that this pseudo-random noise sequence, it takes a bit of amplitude. And if you don't want your ADC to saturate, it means that the blue signal now should have a little smaller amplitude. Otherwise you saturate. You need to make some space for this green signal. So this means you kind of reduce the available dynamic range of the ADC. And normally, in order not to lose too much dynamic range, we usually make this green signal very small in amplitude. But you can imagine if you make the green signal really small, then it's also getting really hard to measure it at the output. And because of that, usually you have to measure quite long at the output. So you can do some averaging to kind of extract the green signal reliably. So that takes you more time and more computation. So a third option to mention of background detection is using a split ADC. So in a split ADC, what you do is you kind of you divide your original ADC in two halves, A and B. They're functionally the same, but they're kind of half the size, and because of that, they take half the power and half the chip area of the original ADC. And if you simply take the average output code of these two, then you get kind of the original ADC behavior, and nothing really changed there. But because you have two halves, you can also look to the difference or the delta between the output codes. And this delta, it will tell you there's some kind of error between the converters. And this is what can help you to do error estimation. So based on this delta information, you can measure different types of errors between the converters, and then you can calibrate it out in the system. So what these different background calibration methods share in common is that they can track errors which are time variant and change over time because it can continuously detect over time. The downside is that you might need to inject a signal, or you might need some additional hardware, or you have certain constraints on your input signal dependent on which scheme you pick. Also, the detection time is usually longer and is a bit more complex because you need to separate the error that you measure from the application signal. And the last downside is that if it is continuously active, this detection, then obviously it's also going to consume power all the time. So it's going to be more power hungry compared to a once and for all foreground detection. So that's kind of the downside. All right, so that's only about detection, but once you measure the error, you know the offset or you know the distortion, you also need to correct it. And there are kind of two schemes. You can do feed forward in the digital domain with post-processing, or you can do a feedback architecture in the analog or mixed signal domain. So with feed forward, it means that, for example, when you have detected the offset, then you simply have a digital block which is subtracting the offset, and then you have compensation. So that's kind of simple and nice. Everything is digital here, so it's kind of easy to implement and reuse. The downside is that this detection now needs to be very precise because you have a feed-forward architecture. For example, if you detect an offset of 5 LSBs, and then the correction will do -5 LSBs, that's okay. But if your detection makes a mistake and you measure 4 LSBs of offset, even though it was 5, then actually the correction will also be a little bit wrong. So the detection really needs to be very precise in measuring the error. In the second case with feedback, what you do is you detect the offset, like this 5 LSBs again, but now you have a feedback and you kind of fine tune and you trim some components to really solve the problem, like the offset, at or near the location in the circuit where it really happens. And you keep on tuning this offset until the output has no offset anymore. So this is kind of a feedback structure. And the nice thing of that is that your detection is now much more simple. Your detection, for example, for offset, it only needs to measure whether the offset is positive or negative. And that's already enough information to tune your offset towards 0. So you don't need to measure the amplitude, the magnitude of the offset precisely. You just need to know the sign of the error. And thanks to the feedback, you can always find the best solution then. And so in other words, the detection here is easier. The downside is that you really have to make this kind of analog tuning feasible. So whenever you make a new converter, you also have to make those circuits for trimming again. Whereas for the digital case, you can more easily reuse that because everything is digital. All right, so those were kind of some general schemes. Now we're going to look to some design examples for the different ADCs I mentioned. just to show you a bit of an idea what is recently being used. So here you find a lot of references, and then you can study further if you want to know a little bit more. So we're going to start with the lower frequency design, starting with the SAR converter, and then we move on to the delta sigma and the higher speed ADCs. So a Nyquist SAR ADC is usually implemented with a switched capacitor network, which is both used to sample the input voltage, but is also used in combination with a comparator and digital logic to do a binary search algorithm. So if you look to the residue voltage on these capacitors, you'll see that this residue goes up and down in every step, with steps that are gradually becoming smaller, showing that we do a binary search. And at the end of the search, you see the residue goes to 0, which implies that you found the right digital output code representing the input voltage. In terms of design for this ADC, the key challenges are with noise and with mismatch. So noise is mostly from the comparator and the duck noise, KT over C type of noise. And in terms of linearity, the biggest issue is the mismatch of these capacitors. They should be binary scaled to make a binary search algorithm. But if there's some mismatch, you get some nonlinearity in the ADC. So those are the most critical issues. So in terms of noise, what can you do about noise? We have seen you cannot calibrate, but you can still use some enhancement techniques. So a first example is chopping. So chopping is a technique which is well known for amplifiers, and there if you do chopping, you essentially modulate, you move your 1 over F noise and offset of the amplifier to a higher frequency out of your bandwidth of interest, and then you can later filter it. So you can use a very similar chopping technique for an ADC. So if you do a chopping around the ADC, you can see an example here. At the input, we sample the signal on the capacitive DA converter. But to make chopping, you see that we now have 2 sets of sampling switches controlled by phi1 or phi2. And in the time domain, if this is the sampling frequency, we alternatingly sample with switches 1 or with switches 2. And if you look to the switches, you will see that switches 2 are kind of reversing the wires. So you're kind of sampling the minus input voltage here. At the output of the ADC, which is digital, you have another chopper which is kind of reversing that operation from the input. So in that way, you have chopping and dechopping. Or if you think as an RF designer, it's a bit like mixing and down mixing. And because of that, you mix up and you mix down. Your original input signal ends up at the same frequency. But the 1 over F noise or the offset inside the ADC, it only passes through a single mixer or chopper. So those are up modulated, but never down modulated. So in the frequency spectrum, what it means is that if you do chopping, and you see that the signal doesn't really change, but the offset and 1 over F noise will be modulated to the chopping frequency, which is half the sampling rate, because that's the period of the phi1 and phi2 signals. So if assuming that you use oversampling, you see that these 1 over F noise and offset are now out of band, so you can eliminate them. Also, what you will see with this kind of chopping is that actually the even order distortions, like second or fourth order distortion, they're also modulated, so they can also be out of band if you have sufficient oversampling. So this is kind of one enhancement technique for random errors. And there are more enhancement techniques in terms of noise. So very quickly here is if you have noise. Of course, if you have noise of a comparator, you could say, okay, let's make a better comparator design, which has less noise, but this will usually cost you more power. Another option that you have is to use more a digital type of algorithm to minimize the impact of noise. So one option is to do so-called majority voting, which is kind of an averaging technique, you could say. What you do here is that you kind of you trigger the comparator several times for the same input signal. And because of noise, it might produce you some zeros and some ones. But then if you look to the majority, if you get more ones than zeros, then the final decision is going to be a 1, for example. And then statistically, you're kind of averaging out the noise as well, and you get a more robust decision. So of course, if you want to do this multiple activations of the comparator, it takes you more time and more power, but you get a better signal-to-noise ratio. So is this efficient? Yes, it can be, because if you look to the SAR conversion principle again, you'll find that in many cases the residue signal which goes to the comparator is very large in amplitude. And in such cases, actually the noise of the comparator doesn't matter, because your signal, your residue is so big, and the noise will not cause a mistake in the decision. So in these cases, you don't need to trigger the comparator several times. You just trigger it once, you get one decision, and it's reliable enough. And only in the last cases here where the residue is really small and then the noise might corrupt the decision, only in those few cases you do this voting scheme. You trigger the comparator several times. So because you only do that here and not for the others, this is why the method can actually be relatively efficient. So that's not all. You see variations of that theme. So here are two other techniques. I will not go so much into detail, but a bit like the majority voting, they try to kind of average the noise of the difficult decisions, or they even try to look into the statistics of how many ones and how many zeros we get to estimate better what the residue is, and in that way you get a better signal-to-noise ratio. So these are kind of digital techniques trying to improve the signal-to-noise ratio in a way that is more efficient than trying to just scale up your analog circuit to get a better signal-to-noise ratio. So those are kind of noise reduction techniques. Another a bit related technique, which is very different, but which can also deal with noise or with other issues in an efficient way, is adding redundancy. So originally we tried to make a binary search algorithm, which means that, for example, if this gray area is the search space at your input signal range, you initially put a decision threshold in the middle, and then you decide a 1 or a 0, and based on that, you're going to search in the upper or the lower half of the original search space to find your next bit. But if you accidentally made a mistake, and you, for example, you thought you are in region 1, but actually you are in region 0, then you can never recover from that because you end up in the wrong range. So if you add redundancy, it means that you add a little bit of overlap, and that means that no matter you decide a 1 or a 0, if your original input is kind of in the middle, near the original decision point, then it doesn't matter whether you pick a 1 or a 0, because there's overlap. So in the next cycle, you can always recover and still find an appropriate digital output code. So this is what we call redundancy. And this is very powerful, because if you make mistakes due to noise or because of some timing issue or some incomplete settling, you can resolve all these issues because you have redundancy in the system. And to implement it's quite easy. Essentially, it means that your binary scaled weights, they need to have some overlap, and you do this typically by either duplicating some values so that you have kind of more weights, or you can also make a non-binary factor. You make a sub-binary radix, as we call this. All right, so that's a bit about the noise techniques. If you go to the capacitive DA converters, where we care about the energy consumption and the matching, we can also see several enhancement techniques. So if you look to a capacitive DAC, essentially it's a switched capacitor network, and the energy consumption of a switched capacitor network is given by this equation here, where CDAC is the total capacitance of the DA converter, Vref squared or VDD squared is kind of the voltage that you apply. So this decides the charge and thus the energy consumption. And the activity factor alpha has to do with how exactly you switch the capacitors, because that also matters for the consumption. So to save power, you can clearly work on these three factors: reduce the supply to the minimum needed, try to minimize the capacitor value, and try to switch the capacitors in a smart way so you don't waste unnecessary energy. And all of these methods are pretty popular to investigate. So I want to show you one example here of how you can reduce the activity factor. So in this example, we want to make a 12-bit ADC, but especially for a 12-bit ADC, the first MSB and the MSB -1 capacitors, they are really big. And if you switch those, it takes quite a bit of energy. So what you do here in this design is there's an assisting ADC, with a very low resolution, a very small capacitor. So in this case, it's a 5-bit assisting ADC having pretty small caps because it's only 5-bit. And after you sample the input voltage, we first use the 5-bit ADC to make a not so precise, but a very cheap 5-bit quantization of the input signal. And then those 5 bits are directly loaded into the first 5 bits of the 12-bit ADC. And then the 12-bit ADC continues to decide the remaining 7 bits to get the final output code. So the benefit of this scheme is that the 5 biggest capacitors in the 12-bit converter, they only need to switch one time when you kind of load the decision from the assisting converter. Whereas traditionally they need to switch 5 times, once for every decision. So because you switch the caps less, this is why it might be more energy efficient. And the downside might be if there's any mismatch between the two converters, you're going to get some kind of major nonlinearity. So to deal with this, typically these kind of assisting converters have some redundancy. And in that way, if there's some mistake between the two converters, as long as that is within the redundancy budget, it doesn't matter, but you can still solve this in the digital side. So this is very popular, as you'll see later in the design examples. So the next one is about the capacitors. So the energy was CV squared related. So smaller capacitor means less energy. So to make smaller capacitors, you can typically use custom layouts. For example, you can make very small fringing or finger capacitors. And then typically you make one unit and you copy the unit and you connect them in binary scaled groups to make nicely binary scaled capacitor arrays. This gives you good matching. It's a well-established approach. But the downside of this technique is that you need an exponential number of units as a function of the number of bits. So it quickly becomes a lot of components, which has a lot of area and a lot of parasitics and a lot of overhead. So another technique you can use is length scaled capacitors. So over here to make a couple of binary scaled bits, bit 0, 1, and 2, we make gradually longer metal strips. And the longer the strip, the higher the capacitance. But you probably know that if you just make the length longer, it doesn't give you very precise scaling. And that is because some parts of the capacitor, like the vias and the corner, for example, they don't scale with the width, but they stay more or less constant. So to make accurate binary scaling, what we do is we have compensating elements for each capacitor. And whenever we switch capacitors C0, for example, the compensating element C0 prime is switched with an opposite polarity. And this opposite polarity is kind of as if you're subtracting the two capacitors from each other. And it means the effective capacitance is given by the delta length, the length difference of the two halves of the capacitor. So that means that if you now make capacitors where the length difference, the delta is scaling with binary steps like 1, 2, and 4 delta, you now exactly get binary scaled effective capacitors because the compensating element will exactly compensate for the vias and the corners which don't scale with the length. And what remains is really, the effective capacitance really only depends on this metal length variation. So this gives you accurate scaling without any issues, without any calibration, for example. So what's the positive part here is that if you want one more bit, you just need one more strip. So it's a linear complexity, whereas the original unit element approach is a exponential complexity in number of components. So this is why delta length will be smaller if you go to higher resolutions. So we try to do this for 10, 12, and 14-bit converters. So here in the picture, for example, you see a 14-bit ADC. You see two 14-bit ADCs actually. The lower one is unit element capacitors and the upper one is delta length capacitors. And you can see that's a lot smaller in the layout, while the total capacitance is actually about the same, about 10 picofarad in both cases. And also the linearity is reasonably similar in both designs. So there's a bit more information about analyzing the performance, but in view of time, I will skip that a little bit. I would like to go to the next topic about these capacitors, and that is that at some point you simply cannot get the matching good enough. No matter how big or small you make the caps, if you go for high resolution, then it's kind of impossible to make your layout precise enough. So this is the point where you start to use calibration techniques. So in this example paper, they use a foreground capacitor calibration. And foreground makes sense because capacitor mismatch is typically something which is very static over time, and it's not so much voltage and temperature dependent. So you can measure it once and then you fix the values. So in this particular design, they use a technique which is also quite popular, and that is you kind of use the smaller bits, the LSBs, to measure the bigger capacitors. And you do this step by step, and you continue with more and more bits. So mathematically, you could see this as like you make kind of a matrix where every capacitor is expressed as a function of other capacitors. And then if you solve the matrix equations, you can find the value for every individual capacitor. That's essentially what you do. So after they do this, then they have measured digitally the value of each capacitor, and then they use a digital post correction, which has a lookup table with the measured weights to do the correction. So in this design, that makes sense because it's a relatively high resolution ADC. And if you remember, higher resolution means digital is favorable. So this is why post correction, digital correction makes sense. So we go here to a second example for capacitor calibration. Same problem, but it's a different solution. So the first one is that the mismatch detection is now in the background rather than the foreground. But the way of measuring is kind of the same as before. So also here we use the smaller bits to measure the bigger bits. And you do this by kind of at the end of the normal SAR conversion where we get the output code A in blue. After that, we add one extra cycle. So we can do this in the background where we kind of force the DA converter to another code B. And in that way, by comparing the A and B outputs, we can kind of compare the MSB capacitor here against the smaller bits. And that's kind of giving you one comparison to be able to get some information about the mismatch. Now, that's one difference. The second difference is the correction. So this is an ADC, which is a bit lower resolution. It's about 11-bit, if I remember. So for 11-bit, a digital correction is kind of too expensive and analog is more efficient. So this is why you see in this paper, the capacitors are trimmed by kind of having a programmable capacitor array, and you can kind of fine tune every capacitor to compensate the mismatch. So this is an analog feedback correction. Now, because it's kind of complex, you need kind of a capacitor array to trim every value. This is not done for all the capacitors because at some point it's just too complex. So it's only done for the 5 biggest capacitors where typically you also have statistically the biggest errors. So that's kind of a compromise to make the complexity acceptable. So those are some different schemes, and you see kind of what the trade-offs are and what the different choices are. So we're gradually now moving to the delta sigma, but we do this by first checking the noise shaping SAR ADCs. So in a SAR ADC, the first thing you can do with a SAR ADC is instead of having Nyquist operation, you can oversample it, which means you choose a sampling rate which is much higher than twice your bandwidth of interest. So by doing that, you make now a large frequency range which is out of band OOB, beyond your bandwidth of interest. So if you do this, you have kind of some space in the spectrum, and you can try to move some problems from your bandwidth of interest to the out-of-band space. So for example, if you can manage to do noise shaping, it means your white noise is kind of shaped, high frequency shaped, so most of it is out of band, and then you can digitally filter this out. And another technique called mismatch error shaping means that you find a way to kind of change this distortion into noise, and also try to high pass filter this such that it appears mostly out of band. So those two techniques try to kind of remove noise and mismatch from inside the band to outside your band of interest. And this, of course, gives you a much better performance inside your bandwidth of interest. So let's see how we do these two techniques, starting with the noise shaping. So later we're going to cover the delta sigma, and if you know it already, delta sigma has typically a low resolution quantizer or ADC, but there's a feedback loop with a loop filter, which is in the form of a low pass filter or integrator. And if you calculate this system, you'll see that this will do a noise shaping where the noise which is introduced by the quantizer or the ADC is high pass shaped, such that you exactly get what I showed you on the previous slide. You can move the noise out of band. So in a noise shaping SAR ADC, you try to do the same thing as this delta sigma. So if you look at the delta sigma, it's kind of like you have a residue that you integrate and put back into the ADC, if I talk in a very simplistic way. So you can do the same thing in a SAR ADC. At the end of the SAR conversion, the voltage on the cap deck is actually the residue voltage. So it's about this voltage in the sigma delta. So if you put this into a loop filter or integrator, H of Z, and then you somehow put this back into the ADC, then you essentially make a loop which is about the same as the delta sigma, and you can achieve noise shaping. So this is kind of the basic idea. The question is then how you implement this kind of loop filter. So this can be done in very simple ways. You can find quite a lot of papers in the recent about 10 years. I just want to show you one example. So the idea people have usually if they make a noise shaping SAR is that the SAR is efficient. So to maintain the efficiency, you also want to make a really simple integrator. So for example, with passive switch capacitor networks or for some very simple amplifiers. So in this paper, what they essentially do is they take the residue from the DA converter, they put this in series with the previously integrated residue, and that means the voltage you get here is the previously integrated residue plus the present residue, so that makes the new integrated residue. And they first buffer it with a source follower, and then they sample that new integrated residue on another capacitor. And every clock cycle, you simply switch C1 and C2, and then the new residue becomes the old residue, sorry, the new integrated residue becomes the old integrated residue, and you get the next one. So simply flipping the capacitors every cycle is good enough to continue integrating the residue. So this makes a very simple integrator. In this paper, they make fourth order noise shaping. So essentially they have 4 of such circuits and they connect them together to make an overall fourth order noise shaping, which means you can move a lot of the noise out of band. So this is very nice and still quite simple. So the second technique is to do something similar, but then instead of moving noise, you want to move mismatch errors out of band. So how to do this? If you have a switch capacitor DA converter and you have mismatch, it means that you get a certain error in the conversion because of mismatch. And if you want to do mismatch error shaping, the idea is that you try to replicate that error the next sample, but then with a minus sign, because this mathematically becomes a high pass filter like this equation here. So to get this minus error term in the next conversion actually has a kind of surprisingly similar, simple implementation. Essentially what you do is at the sampling phase of the converter, normally the digital code is reset to 0, but to do this minus epsilon, you keep the capacitors at the previous code when you sample, and only after sampling, you return it to the 0 code. And in that way, you get a kind of a minus x term, where x is the previous code. And because the previous code also includes the mismatch, you also get a minus epsilon term here. And that's how you get this mismatch error shaping. So to quickly show you that the implementation can be quite simple, over here you see a SAR ADC which has both noise shaping and mismatch error shaping. So the black components give you a normal SAR converter, and then the blue part is doing second order noise shaping. So in this case, we sample the residue of the DA converter. We first amplify this, and then there's a switched capacitor network, which is doing second order passive integration, and in that way, second order noise shaping. For the mismatch error shaping, you can't really see anything here because it just has to do with the timing of the switches in the DA converter, but that's also included. And as a result, the mismatch errors of the capacitors are relaxed, and you can use much smaller capacitors to save power. All right, so this brings us to the sigma delta ADC. So we've already seen this architecture. The key challenges are typically the DA converter and the input stage of the loop filter because they're kind of almost directly connected to the input. So the errors are also almost directly input referred. And both in terms of noise and in terms of distortion, this is critical. So for the DA converter, if you have a 1-bit DA converter, this will be always linear. But if you have a multi-bit DA converter, for example, a 2-bit feedback DA converter, if there's some mismatch, then your transfer curve is nonlinear and you get some distortion in the spectrum. So if you do dynamic element matching, for example, you can randomize which component of the DA converter you use at which position, and you're kind of arbitrarily switching between different transfer curves. For example, you're kind of alternating between the red and the green curve. So if you do this kind of random, this assignment, then the average curve is going to be perfectly linear always, but these individual variations will still show up, but at a random position, and that means it will show up as noise. So this kind of dynamic element matching essentially is removing the distortion and it's changing it into a random noise floor. So this is nice. You can do a little bit better than this, and instead of doing kind of random selection of the elements, you can do a certain rotation scheme where you select them in a certain order. And if you do this wisely, then you don't just make it white noise, but you make it kind of shaped noise, which is nice if you combine it with oversampling, so you get a much better in-band performance, pretty much like the error shaping in the noise shaping SAR. So to see this in practice, over here you see a sigma delta modulator where you see several forms of enhancement and calibration. It's a continuous time RC-based integrator sigma delta. So the first thing they do is they trim the capacitors in order to trim the RC product of the integrator. And this is relevant in industry because over process corners, the RC product can change quite a bit. And to compensate for that, they trim the capacitors. The second thing they do is because it's a multi-bit ADC and multi-bit DA converter, the DA converter can be nonlinear because of mismatch. So they use some kind of dynamic element matching indeed to randomize the errors. Now this is not good enough in this paper because in this work the oversampling ratio is quite small. So even if you randomize and make the errors noise-like, you kind of still have too much noise in band. So to do even better, they also have a calibration, a digital post-calibration to kind of really detect the mismatches of the DAC components and to do a post-correction to really fully compensate it. And this way they get even better performance. So something similar is done in the ADC. So typically the quantizer mismatch in the sigma delta is not so critical because it is noise shaped. But again, in this design with a low oversampling ratio, that's still not good enough. They also need to make the errors in the quantizer smaller. So it's a multi-bit quantizer, as you see here, with several comparators. So the first thing to get rid of the nonlinearities of the quantizer, which is essentially because of the offsets of the comparators, they randomize or they shuffle the references, which essentially means that these different comparators are kind of used in different positions in the flash converter. And by kind of randomizing the position, you also linearize the quantizer. On top of that, they also look to the output statistics. If you randomize the comparators, the output statistics should also be the same. If they are different, it will tell you something about the offset, and thus you can calibrate it. And in this way, they make it even more linear. So here you see nice kind of combinations of randomization plus calibration in order to really together eliminate the errors. So that was about the lower frequency designs, and we now quickly move on to the higher frequency designs. So pipeline converters are ADCs where You divide the total resolution over many different steps. Every step resolves a couple of bits, and then digitally you combine all those contributions to get the final output code. The nice thing is that you can get high resolution because every step just needs a couple of bits or maybe only one bit. It's also high speed because you sample between the steps. So every step can work at the same time on a different input signal, and you can get a very high throughput. A main positive side of this pipeline is that you have an amplifier at every stage. And thanks to this first amplifier, for example, all the mistakes made in the later stages are less critical, because if you refer the noise or the distortion from those stages to the input, you can divide it by this gain, and that's why it's less critical. So it's mostly the first stage which is the most critical issue. So it's already for long that people calibrate pipeline converters, because you have many stages, many components, you can have many issues. So already like 20, 30 years ago, people calibrate offsets and gain errors. But usually they didn't calibrate distortion yet because it's kind of complex issue to fix. Now, in more recent work, you see people also start to deal with distortion. And because of that, they can also use residue amplifiers in the pipeline, which are more efficient, for example, open loop amplifiers. So in this example here, you see a pipeline converter, which is also time interleaved. It is made with 5 stages, each solving 2 bits. And between those stages, you have residue amplifiers. So the residue amps typically take a lot of power. So here they want to make a efficient amplifier, and they use an open loop dynamic amplifier for that. And I'm only showing you a little part of that amplifier. So those amplifiers are efficient, but the downside is that they have gain, offset, and distortion, and those are also sensitive with the voltage and the temperature. So that means you need to calibrate it. And the way they do it is they make several components in each amplifier tunable, so they can tune the offset, the gain, and the distortion. And then they use this split ADC architecture I talked about earlier to detect the individual errors. And then they separate this information to be able to control every single amplifier in the pipeline to eliminate their gain, offset, and distortion. So you can imagine it's quite complex, but as a result, they get a very efficient ADC. So that's about pipelines. If you go to time interleaved converters, you have all the problems I mentioned before in the individual converters, but you also have issues that in time interleaving, you have parallel ADCs, and they should ideally all be the same, but you always have mismatches between those channels, and they give you additional spurious components. So if you want to calibrate that, there's a lot of issues to deal with. So to show you one issue is the time skew. So the time skew is if one channel is sampling a little bit too late in comparison to other channels. So to deal with that, pseudo-random noise injection is one of the popular techniques. So this is something we also saw before. So what they do here is they make a pseudo-random noise sequence with 0 and 1 or plus and minus 1. But because a square wave is not very useful to detect the time skew, they kind of convert this pseudo-random noise sequence to something which has ramps. So you get either a positive or a negative ramp, dependent on the bit is a 1 or a 0. And this goes into the ADC, the time interleaved ADC. So why they do it like this? Because now if suppose this is the desired sampling point, the nominal, but if there's some time skew and you sample a bit too late, then you see that if you have a positive slope, if you sample too late, you get a positive error, epsilon. But if you have a negative bit, sorry, a 0 bit, and you have a negative slope, you get a minus error. So if you have this pseudo-random noise sequence and you have this kind of positive and negative slopes, if you inject this into the ADC, then at the output you can do a correlation, and then you can extract the timing error because you know exactly when you inject a positive and a negative slope. So based on that, you can extract digitally the time skew of every channel. And then by kind of fine-tuning a delay line, you can compensate the time skew of every sub-ADC and compensate for that. So this is where you see the pseudo-random noise sequence in action. Now this one only deals with time skew. If you put everything together, you get kind of amazing and complex systems. So over here, you see an example of a time-interleaved pipeline converter. And here they inject pseudo-random noise sequence in many different locations of different types. And then digitally, they can kind of separate this in order to measure different errors like the timing or the gain errors or the distortion. So it's very complex, but in this way, you see it's kind of one type of scheme to detect different errors at the same time. So that's a bit about the calibration schemes. Very quickly, in view of time, something about digital-inspired analog circuits. So far we saw enhancement, but you also see that people try to get inspired of how digital circuits are designed and try to use this for analog circuit design because it might be better in terms of scalability. So a couple of examples. One is the so-called inverter-based amplifiers. An inverter is maybe originally a digital circuit, but it's also a very efficient amplifier because you get twice the transconductance for a given bias current. So there are many efficient amplifiers now based on an inverter, like just an inverter or a floating inverter or a ring amplifier. They're all on the principle of this using an inverter as an efficient amplifier. Other options are to use more frequency or time domain circuits. So a VCO is a voltage controlled oscillator where you change the voltage information to the frequency or to the phase domain. And especially if you look to the phase is actually an integration of the frequency. And because of that integration, a VCO can also work as an integrator or a noise shaper. So a way you can use this is, for example, if you make a sigma delta, in this case here, instead of using a classical integrator, you see that the integrators are made with VCOs, which have this first order integrator. So you see 3 VCOs and it makes a third order noise shaping sigma delta converter. So here you see kind of a nice mix of using a digital scalable technique in a classical analog architecture. And then the final one is using time-based information processing. So you can change your voltage information to time pulse duration, and then instead of having a voltage-based ADC, you now need a time to digital converter, which is a circuit which kind of measures a time duration and makes a digital output proportional to this. So the idea here is that with low supply voltages, it might make sense to put information in the time rather than the voltage domain. So you see now in designs that they kind of use hybrid solutions where part of the ADC works in the voltage and part works in the time domain, and this gives you kind of nice benefits of both approaches. So quickly, a bit of an outlook and a conclusion. So we see that there's kind of need for calibration, especially for the higher speed designs and the high resolution designs. So it's kind of questionable, how do we move forward? How do we deal with the complexity? And can we also maybe make more efficient converters by using, instead of the standard way of filtering, sampling, and quantization, maybe other approaches which are more efficient in terms of dealing with the signals. Some future challenges that we see here is that you see the converters I show you are kind of getting complex. It's not just the analog circuit design, but you also have calibration. You see a mixture of different principles in the circuits. So the design is getting complex, and you can imagine also the simulation is getting very hard because it takes a long simulation time, especially with these calibration techniques. And it's very difficult to make suitable models. And this also leads a bit to the question, should we make all this calibration just for the ADC? Or maybe we should calibrate a whole system at once, and then you can maybe use the same calibration infrastructure to deal with multiple issues in a bigger system. So that's a bit the outline for today. So I think I hope I convinced you that these enhancement or calibration techniques are essential, especially for high-speed design like pipelines and time-interleaved converters that all pretty much use these calibration techniques. It's also important to realize that they're not for free, so please still be careful about when to use them and to what extent to use them. Otherwise, they might turn out more costly than you expected. And it's also important to think about what do you move to the analog and what do you move to the digital side of the equation. And so overall, as a modern designer of ADCs, And you should not only be able to really design the circuits, but also you need to make the right decisions and the right implementations of these enhancement techniques. So that makes it exciting, but also very complex. So I think that's concluding my talk. I think I'm a little bit over time, but I would like to thank you very much for your attention, and I'll be very happy to answer any questions or discussions that you like to have. Thank you very much.
So we are going to open the space for any questions we can have. So who wants to start, make a question?
Okay. Hi, Peter. Here, well, first of all, thanks for your presentation. I'm currently working in ADCs too, in noise shaping ADCs, and my thesis is mainly focusing on area reduction strategies. And when you are starting to look for how to reduce the area of an ADC, you find that in the literature, it's not so common to take into consideration the area. For example, in the figure of merit, you only take into consideration power, resolution, frequency, sampling frequency, but it's not so common to take into consideration the area. What's the reason of that problem? Why does the literature doesn't take into consideration the area?
Yeah, it's a very good question. So why not? It's maybe a little bit because there's kind of a reasonably fundamental relationship between power, noise, and bandwidth, and that's kind of also the three factors you have in the figure of merit. And it's a bit of a it's a bit of a self-fulfilling prophecy that a lot of people focus on the figure of merit, and because of that, they might not look to the area. However, if you go to a company and you make a product, then actually area is often important because it is a cost in the end, right? So maybe indeed, I fully agree with you that in a lot of papers you don't see a lot of attention about area, but especially from industry point of view, I think it is definitely a very relevant subject. The trouble is that it's not something so easy to put in a so-called figure of merit because it's very hard to say how the area scales with the other metrics. It may or it may not. So that would also not exactly be fair. So I think it's really an independent parameter that should be valued, so to say. So I think it is relevant. I think it is nice that you do it because it's more original than what the majority of people maybe are looking for. So I think it's definitely nice. But it might indeed mean you have to make your own, let's say, somewhat models, so to say, to kind of estimate which design directions are suitable to reach the smaller area in the end. And as you probably also know, it's sometimes a bit surprising which components are big or small. Or like in my converters, I often see that the overhead of wiring is often important if you don't do this well. So it depends a lot on your technology and your layout style also, what is the critical factor. And then a bit related answer is that if you look to many ADCs, let me see if I can find it. Here, SAR converters, right? So over here, for example, the duct is large, but the wiring is larger. But then often the reference voltage or the supply decoupling is even much larger than the converter. So do you account for this or not, or is it external? So those are also relevant questions when you consider the area or, let's say, the total size of your design. But I think in general, I think it is really nice if you do a study where you can indeed see which directions, which decisions really help you to make smaller area. I think that is very, very useful.
Anyone has a question? Let me ask you a question, Peter. You talk about calibration techniques, and you mentioned backward and forward calibration. Let me ask you if the calibration is performed, as I understand, after fabrication, so how, if you're performing background calibration, how do you guarantee the calibration does not affect the signal processing of the ADC in the moment? I mean, because the idea is to don't stop the ADC for the task it's doing. So how can you guarantee that it's not perturbed?
Yeah. That's a really good one, and it's maybe indeed hard to prove, right? Because indeed with a simulation, sometimes you can't always see it. But like indeed, if you see the bottom right picture here, where the blue one is your application signal, for example, and the green one is your extra signal you put in to do this background calibration. And indeed, ideally, they should be perfectly separated from each other, but you can't do this in these, so they kind of influence each other. And so, for example, what you see in papers that do this is that sometimes the measured spectrum, which ideally should only show the blue signal, it will probably get a bit of extra noise or maybe some glitches, which is kind of a residue from this green signal. So it's usually a bit worse. So some papers measure this intentionally, and they kind of measure the performance with this noise sequence, the green signal turned on and turned off, and then often you see a little bit of performance degradation indeed when the green signal is turned on. But people try to make that impact smaller by, for example, using a small amplitude green signal so it doesn't do too much on the blue signal. It also is vice versa, and that is that, if your blue signal has, how to say that, if it has some kind of components which are kind of similar to the green signal, then your detection might fail because it might confuse the blue signal as being a green signal, and then your detection will go in the wrong way, or it might take more averaging to kind of correctly separate them. And that's because, we use a pseudo-random noise sequence, but many people use pseudo-random noise sequence, right? So maybe the signal that you process is also a pseudo-random noise sequence. And if you have bad luck, there's kind of some correlation between them, and this will entirely make your calibration going wrong. So it's indeed kind of difficult, and so many calibrations have some limitation that indeed they have certain patterns for which it doesn't work, for example. So they might still have a little bit of signal constraints. And in industry, for sure, they're also a little bit careful, because if in industry you sell a chip, you want it to work for every customer, no matter what your customer is going to do with that converter. So, and the background detection in that sense is a little bit of a risk in a certain way, that maybe if the consumer that buys your chip is putting in some signal that is kind of interfering with your calibration, or maybe they measure something at the output and they see a bit of residue from your calibration, they might not be so happy. So it's kind of quite a tricky process to do this really, really very good. So I think if you design these techniques, you for sure need to do, I would say, some, let's call it behavioral model simulation. So you can do kind of long and accurate simulations with many different test signals to see how it behaves over different types of inputs. But the behavioral model, of course, is simplified. So, but the problem is that the circuit level simulation, you really cannot simulate this too well, because these sequences take a long time to, like tens of thousands or hundreds of thousands of samples to get something out. But in the circuit simulator, you can simply never simulate so long, probably. It's just too slow. So that's kind of the complexity.
Thank you, Peter. And I don't know if there is anyone. Okay.
Good afternoon, Peter. In the last slides, I see something about AI-based calibration. And my question is, are there practical AI-based calibration techniques today? And how do you envision this approach pushing the limits of the next generation of IDCs?
Yeah, thanks a lot. Yeah, indeed, I went a bit quick here because I knew I was a bit late. I'm sorry. And so indeed, of course, AI is kind of a very active research topic for many reasons at the moment, right? So it's a little bit of a hype maybe and a little bit of a use case. So logically also with the calibration schemes that I showed you, see it's getting more and more complex. And this is why I think there's also interest to see if AI can play a role. I think it is still very early stages. You see, if you look around on IEEE website, for example, you can find a few papers about using AI for ADC calibration, but it's really not so many. As some are a bit more theoretical or a bit more based on simulations, but not really on measurements. So I think it is early stage research, but I'm pretty sure that there are quite a lot of groups looking into this. I think the main challenge here is going to be that ADCs are really very efficient and you really can't afford a lot of digital blocks before you start to completely overwhelm your ADC performance with a lot of digital power. And the challenge, I think, is how to make an AI system which is very simple and efficient. Otherwise, it's going to be way overkill to the ADC. And then I'm not even talking yet about how do you train it, for example, to make sure that it's always correcting what you want. So in my opinion, I think it can be relevant, especially for maybe if you have like systems like this here, where the calibration is getting really complex because maybe you have many components you want to calibrate, and you have many amplifiers, many error sources, and at some point it becomes really hard to, let's say, make a dedicated calibration method for every single item. And instead, maybe you say, okay, let's put everything together and have one AI network which can deal with many issues at the same time. Or if the issues are getting so complex that you can't really define individual calibrations for each of them. I think for such complex systems, the AI might be a way forward. But then the question is still going to be how to make it simple and efficient so that it doesn't completely ruin your efficiency performance, so to say. And I would expect in the coming years that we see a bit there. Having said that, I think the majority is still going to stay with the more conventional calibration, I would expect, simply because that gives you a better optimization of efficiency, I would expect, because you really optimize it for a certain task. And I think that's still better as long as that is feasible.
Okay. Any another two more questions. The first one, it's well, it's similar to the question of the area. It's a similar gap related to the area. Well, not to the area. The reference voltage generation that is usually used, for example, in the SARI disease. It's another topic that isn't too much mentioned in the papers, in the literature.
Yep.
And the other question, first, what's your opinion about that gap? And the other question is about, you said about that it's very, very helpful to start using digital inspired architectures. What about the fully digital implementations, like the synthesizable ADCs? What's your opinion about them?
Yeah, thanks a lot. So the first one about the reference voltages. So indeed, dependent on the architecture, but for example, indeed for the SAR, where you have a switched capacitor network that is connected to your reference voltage, it's a very nasty load for the reference driver because you connect switches and capacitors, you have very high peak currents, but the reference should stay kind of precise. And as a result, you need a lot of power in this reference driver, or you need a lot of decoupling capacitor to stabilize it. So indeed, this is a power or area issue. And I fully agree that's a relevant topic because it is, if you're not careful, this will definitely consume more area than your whole ADC. And the power is also not always negligible. So there are some papers that try to kind of look at that or to combine the reference with the ADC design in a smart way. I think that's very useful because I think that let's say, it's good that we look a bit beyond the core ADC context, but really look to the system around it, because there are bottlenecks which are much more important, like this reference. So I don't think there are really kind of very good established solutions yet for the reference. And like I mentioned, there are some papers that try to assess it. I think there were some nice ideas, but none of those became really mainstream. So that means that still there is work to do, I think, until people really have very, very great solutions about how to do the reference. And if everybody's convinced about it, then I think a lot of people will start doing the same ID. And then it becomes kind of second nature and part of the ADC design, which I think will really show progress. So I hope we will get there at some point, but it means there's still work to be done. The same is true, for example, for the input signal driver, like whatever is at the input here has to drive a switch capacitor, for example. So for high-speed designs, typically this buffer is included, like you see here. But for many low-speed designs, like the SAR converter beginning, where is it here? There's no input buffer included in the chip usually, but this is kind of difficult because it's driving, again, a switch cab load. So also making those input drivers efficient and smart, that they can deal with the capacitive load without consuming a lot of bias current. I think those are very interesting research topic, because at the system level, that's often more critical than the ADC is. So I think it's a very good topic. The second question you had was, I forgot it now. Can you remind me? Or about digital synthesis, for example, digital synthesis designs, I remember now.
Digital.
Yeah. Yeah. It has two sides to it, I think. So these are kind of, let's say, I would say it's kind of early research work in a certain way, in the sense that it's kind of really an exploration going beyond the, yeah, let's call it stepwise improvements of ADCs, is really a milestone further away, trying to really look to different new type of methods to make an ADC. And because they're so far out, I think at the moment they're not yet so attractive, maybe in terms of performance. And the question is if there's going to be enough research to make them kind of comparable or even favorable compared to the conventional designs. So there's a lot of work needed to do that. And the question is if they're going to get that improvement or they're not going to get this. So that's a bit hard to say. Personally, from what I've seen at the moment, I think that often it's kind of a balanced method, which is nice. And I will show you some other examples in a second. But a few things to say. If you look over the past years, for example, the noise shaping SAR, which is here on the screen, maybe you remember the very first noise shaping SAR from Vredenberg. That first noise shaping SAR was not that great in terms of performance. It got an ENOP, I think, which was lower than the SAR quantizer was, or similar, and the noise shaping helped, but really not so much. So if you just look to the performance of that paper, you might say, well, it's not so promising. But I think the promising part is that it's a nice concept. And many years later, lots of people work on the noise shaping SAR. They get a lot of performance improvement. And then because of so many people working on that, it becomes attractive and it gets a performance which is actually at the state of the art. So I think it can happen, but only if indeed it gets enough traction and people start to figure out how to do it in a way that it makes it really competitive. And you see a bit the same with other innovations, like, for example, the VCO-based ADCs. So the original ones, they just use VCO, and that's kind of the ADC. But that's not really so attractive because it has a lot of process, voltage, temperature sensitivity. VCO is very nonlinear as well. So it, as an ADC standalone, it kind of gives you all sorts of issues. But then, for example, you see this when you put this in a feedback loop and the issues get less important for the overall performance, then all of a sudden it might start to make sense. Same thing with the time domain circuits. In the early works with time domain, people said, okay, let's just move everything from voltage to time and that's it. And then we do time to digital converter. This might, in my opinion, be a little bit too extreme because if you don't put any information in the voltage domain, but you move all your information to the time domain, you're kind of wasting the ability your voltage dimension has. And it's better to have a little bit of bits in the voltage domain, I think. And that's also what you see with these wireless communication standards, right? In the old days, it was 1-bit modulation, but at some point people said, well, we can put a few bits in amplitude, a little bit of voltage variation. Why? Because that is the first couple of levels are kind of cheap to get, so it would be a little bit of waste not to use them. So that's why I think purely time domain, I don't think is the best way. I think the best way is having a little bit of a mix. And that's maybe why on the right-hand side, you also see an example where I think the designers really think about, okay, let's not just do everything time, but let's try to use the time where the time is good and then use the voltage where the voltage is good. So you really see a mixture. And that's also what with digital synthesis I would expect. Maybe not everything digital synthesis or fully digital, but maybe also some sort of a hybrid with large parts maybe digital, but there might still be some key blocks analog in order, let's say, to have a good balance or good hybrid combination to get the best of both worlds. That's at the moment a bit my feeling, but it's really more an opinion than really a knowledge at that point, right? So we're going to see what the future will bring.
Thank you so much, Peter. So the time has over for the questions. So one more time, Peter, we all want to thank you for being here with us today. And please, we are going to take some minutes for a quick picture. So, but I want for all of us can give the thanks to Peter.
Thank you very much, and to everyone, good luck with your studies and your projects.
Peter, can you stop sharing your screen so you can be full screen here, please?
Yeah. 1 second, I need to...
People have joined in the stream, so we are going to close the talk here. Thank you so much for attending.
This is a little bit large, isn't it?